It's Friday evening, and Daniel wires the refund tool into the support desk's agent because customers shouldn't wait a day for obvious refunds. It works, and nobody thinks about it again. On Monday, a ticket arrives carrying hidden text the customer never wrote, telling the model to ignore its instructions and refund the order in full. It nearly fires, and Priya, who owns the queue, says the sentence this whole exam is built out of. Ticket text must never be able to trigger that tool. Freeze right there, because the Claude Certified Developer exam writes its 53 questions out of moments, exactly like this one. Here is Priya's Monday, written the way the exam will write it. Ticket text submitted by customers must never be able to trigger the refund tool. Which approach satisfies the requirement? 4 options, and every one of them sounds sensible. Add a line to the system prompt telling the model to ignore any instructions found inside tickets. Switch to the most capable model tier since it follows its instructions more reliably. Treat ticket text as untrusted input and put a blocking approval hook in front of the refund tool. Or set the sampling temperature to 0 so the model behaves predictably. 3 of those 4 die in about 4 seconds for exactly 2 reasons, and both reasons are printed in the exam guide itself. By the end of this episode, you'll kill them the same way, on any question this exam can ask you. That question parks in the corner until you are holding this episode's 2 tools. First, the promise, because this is episode 1 of a full course on the Claude Certified Developer Foundations exam. The guarantee is specific. The exam guide lists 25 weighted skill statements, and this course teaches every single one. Every episode names the skills it carries and what they're worth in questions, and you'll watch that counter fill as we go. Every question on this exam is one of 4 decisions you make when you build with Claude, and the 4 are almost perfect quarters of the whole thing. That's not a study trick, it's just what building looks like. So let's walk them with the support desk in hand. Decision 1. What runs? Workflow or agent, one loop, or a supervisor handing work to smaller agents called sub-agents, and whether a capability is built in, written by you, or plugged in from outside. When Daniel wired the refund tool into the loop, he was inside this decision, whether he noticed or not. That's the agent's domain plus the tool's domain. Call it 13 of your 53 questions. Decision 2. How does it call Claude? The messages you send, whether the answer streams or arrives at once, real time or batch, which model tier, and what the whole thing costs in tokens. It's the wire between your code and the model, and the exam cares about every property of that wire. Call it another 12 of your 53. Decision 3. What does Claude see and say? What lands in the context window, the working space the model reads from, how the prompt is built, and whether the output comes back in a shape your code can actually consume. Priya's desk answers a customer in prose, and it feeds a dashboard in a schema, and both of those are this decision. Prompting, context, app design, and configuration, again about 13 questions. Decision 4. Will it survive production? Requirements and life cycle, debugging when it breaks, and security when someone feeds it a ticket like Priya's. It's the biggest quarter, 14 or so questions, and a surprising slice of it has nothing to do with Claude at all. That story belongs to episode 4. From here on, every worked question in this course gets stamped with which decision it's asking, and that stamp is half the answer. But naming the decision only sorts the options, and sorting isn't killing. So here are the 2 rules that finish. Here is the part almost nobody uses. The guide publishes 3 sample questions with its own reasoning attached, so the exam has already shown you how it grades. Watch its first sample, 10,000 documents processed overnight. Cost is the main concern, and nobody needs results until morning. Read that stem again and notice it handed you the constraint 3 times. Overnight. Cost. Not urgent. The right answer is the batch lane, because it's the mechanism that exists for exactly that constraint. Batch means you hand over the whole pile at once and collect finished results later, which is exactly what an overnight job wants. And look at how the guide's own rationale kills the other three, because they're all knobs. Run it in parallel, cap the tokens, shrink the model. Rule 1 said the way you'll use it. The stem names its constraint. The answer is the mechanism built for it, and a generic knob is always a distractor. That's rule 1, and rule 2 handles the questions where the stem stops describing and starts demanding. The guide's second sample is a page summarizer that gets fed hidden instructions, which you'll notice is Priya's Monday wearing different clothes. That attack has a name, prompt injection, and the security quarter of this exam keeps coming back to it. Its rationale contains the most valuable sentence in the whole document. A polite request is not an enforceable control. Asking users to behave, asking the model to be careful, writing the rule down, all of that is guidance. Guidance is words in the path of something that can ignore words. A mechanism doesn't care what anyone meant. Isolation, a blocking hook, a schema, the output must satisfy. Something actually stops. So, rule 2, when the stem says must, never, always, or cannot, every option that offers guidance is a distractor and only a mechanism can survive. A polite request isn't a control. The exam wrote that grading logic down, and this course will use it on every worked question. Two rules in hand. Now look at what you'll swing them at, because the exam structure is published in advance. Here is the exam as one picture, and it should change how you study. Underneath the four quarters, the guide publishes 8 domains, and under those 25 skill statements, each with its own printed weight. Items are written against those statements, so the exam isn't a vibe, it's a list, and a list can be worked through. The coverage map in the description is that exact list with an episode number against every line, and if a line ever has no episode, hold me to it. And some items ask for more than one answer, and each item tells you how many to select, so read that line every time. Your score report shows a percentage per domain, and this course's practice exams score you the same way, so a weak quarter becomes a rewatch list. One practical door check, said plainly once. Registration currently runs through Anthropic's Partner Academy, which means a company email on a recognized partner domain. If your employer isn't in the network yet, that's the conversation to have first, and the entry tier costs an organization nothing to join. You'll also notice I never say the fee, the time limit, the pass mark, or the retake rules here or anywhere, because they've all moved before. They live in the description and the cheat sheet, where they can be fixed the day they change. So now let's go kill those options. Here is Priya's question back at full size, and this time you are armed. First, name the decision. The stem is about what a hostile input is allowed to make the system do. So this is a will it survive production question. Now find the demand. The stem says must never, so rule 2 is live, and every piece of guidance on the page is already dead. The system prompt line is guidance. It's words in the path of a model that can be talked out of them, which is the exact attack in play. Rule 1 finishes the job because 2 of the remaining options are knobs. Temperature has nothing to do with injection, and the guide's own rationale warns that a model which follows instructions better can follow the injected ones better too. The stem named its constraint untrusted input touching a dangerous tool, and only one option is the mechanism built for it. Treat the ticket as untrusted, keep it away from the instructions, and put a blocking hook in front of the refund tool. A blocking hook is code that runs before the tool fires and can refuse it, and code can't be talked out of anything. 3 options, 2 rules, 4 seconds, and Priya can finally say never and mean it. Notice what you never needed. No product trivia, no version numbers, no memorized flag. You needed the decision you were inside and 2 rules the exam itself showed you. And that's the shape of most of this exam. Here is what you carry out of episode 1. Every question is one of 4 decisions, so name the decision first, then let the constraint do the killing. Rule 1, match the mechanism to the named constraint, and Rule 2, a polite request isn't a control. The coverage counter starts filling next episode, where every build starts with 1 ticket and 1 API call. It's 6:40 in the morning and the support queue is a wall of unread tickets. The same wall Priya climbs by hand every day before anyone else logs in. Daniel's answer is 11 lines of code, one API call, ticket text in, summary out. He runs it on the first ticket and the summary comes back reading beautifully, right up until it cuts off in the middle of a sentence. Freeze, because this exact moment is where the exam's biggest quarter begins. Your first call came back half a summary. So, what happened and which part of the response tells you? By the end of this episode, you'll read that answer straight off the response and you'll know what the model actually does with your text. And you'll know the one thing this API never does. Call it 5 of your 53 questions, and the first segment of the coverage ring starts filling today. Before the call makes sense, watch what the thing on the other end actually does because it's simpler and stranger than people expect. The model writes its answer one small piece at a time, and each piece is picked from the plausible next pieces, one of several given everything so far. That's the whole trick. There is no plan sitting behind it, just next piece, next piece, next piece at incredible speed. Those pieces are called tokens, and they're not words. They're chunks of a few characters each, sometimes a word, often a fragment of one. Tokens are the unit everything is measured in. What you send is counted in them, what comes back is counted in them, and what you pay is counted in them. All of those tokens live inside one workspace called the context window, and here is the part people miss. The window holds more than your input, your request, any tools you've described, and the answer being generated all share the same space. So the window is the model's entire world for this one call. If something isn't in it, it doesn't exist over there. Now the call itself, because its shape is the same in every application you'll ever build. You send a list of messages, each one tagged with a role, and the roles alternate, your turn, the model's turn, your turn. And if you ever send two of your turns in a row, the API quietly folds them into one turn instead of erroring. Each message carries content, which can be plain text or a list of typed blocks, and plain text is just a short way of writing a one block list. Standing instructions, like summarize in 3 lines and never invent order numbers, don't go in the conversation at all. They write in a separate field called system above the messages, which is exactly where Daniel's summarize instruction belongs. And one field is required on every single call. Max tokens, the most misunderstood dial in the whole API. Max tokens is a ceiling, not a target. The model may stop long before it, but it can never go past it. Which solves Daniel's morning mystery because every response carries a field that says why the model stopped. It's called stop reason, and his says max tokens. The summary didn't fail, it hit the ceiling, he said mid sentence. A healthy response says and turn the model finished its thought. He says the budget ran out first. The fix is 2 lines. Raise the ceiling and check stop reason on every call, because a truncated answer that nobody notices is worse than an error. While you are reading fields, read one more, because every response also carries a receipt. It's called usage, and it tells you exactly how many tokens came in and how many went out, which is exactly what you'll be billed for. Get in the habit now. Stop reason says whether the answer is whole, usage says what it cost, and both are free to read. The call works, the summary is whole, and that's when Priya asks for something that sounds trivial and isn't. She runs the same ticket twice to check the tool and gets 2 different summaries, same input, same everything, different words. That's not a bug, that's what next piece at a time generation is like. The model samples among plausible continuations, so identical requests can land on different phrasings. And before you reach for the old advice, know that the dial people used to turn for this is called temperature. It never actually promised identical output, and the newest models have removed it entirely. The concept survived, the knob didn't, and the exam knows the difference. So here is the exam asking about Priya's morning, and this one's worth pausing on because it kills 3 options with the tools you already have. A regression test must verify the summarizer's output on every build, same ticket in passing reliably. What should the developer do? Option 1. Set the sampling controls for deterministic output. Option 2. Assert on the structure and required content of the response, not its exact wording. Option 3. Switch to a smaller model for consistency. Option 4. Lower max tokens so there's less room for variation. Rule 1 from episode 1. Find the named constraint, which here is a test that passes reliably. A smaller model is a generic knob that doesn't even address that constraint, so it dies on rule 1. And a shorter ceiling is the exact move that cut Daniel's summary off mid-sentence this morning, so that one dies twice. Option 1 dies on a documented fact. Even at its most conservative setting, output was never guaranteed identical, and current models reject those controls outright. What survives is the option that works with the model's nature instead of against it. Assert on structure and required content because wording is weather. Design for variation instead of forbidding it. That instinct alone is worth a question or two on your 53. Then comes the moment that rewires how you think about this API. Priya reads a summary and replies, "And what about the refund part?" And the model answers as if it has never seen the ticket in its life. Because it hasn't. The API keeps no memory of your last call. None. Every request starts from nothing. There is no session on the other side, no conversation being tracked, nothing to reconnect to, state-laced, flat. So how does every chat you've ever used remember things? You've already seen the answer. It's the messages list. A conversation is you sending turn 1 and its reply and the new question, all of it, every single time. The model's memory is the request you build. You carry the history, you resend it, and the model reads the whole thing fresh each call. Say it the way the exam will test it. The API is stateless, and multi-turn conversation means resending prior turns in every request. And now the context window from earlier stops being trivia because a growing conversation is a growing request, and the window is where it all has to fit. That pressure, what to keep, what to cut, what to summarize, gets 2 entire episodes later in this course. One more tool before the close, because Daniel's summaries are correct, but the format wanders. Instead of describing the format harder, he shows it, one tiny ticket and its perfect summary, placed right in the prompt. Showing beats, describing examples are one of the most reliable ways to steer this model, and they're cheap. The exam guide calls this zero shot, single shot, and multi-shot, which just counts the examples, none, one, or several. The docs mostly say few shot or multi-shot for the same idea, so don't let the vocabulary rattle you on exam day. Here's what the support desk taught you today. The model writes one token at a time inside one window, and that window is its entire world. A call is messages plus system plus a ceiling, and stop, reason, and usage are the receipts you check every time. Same input doesn't mean same output, so design for variation instead of forbidding it. And the API forgets everything, so the memory of a conversation is the request you rebuild. The counter starts at 5 of 53, and tomorrow Priya wants this thing live in the console with tickets that arrive as screenshots. It's Monday morning and the desk goes live, and Daniel watches his own tool meet its first real agents. A long ticket goes in, the screen holds a spinner in silence, and the agent decides it's broken and runs it again twice. Then a ticket arrives as a screenshot of an error message, and the summary comes back confident and useless. This ticket appears to be empty. Priya hands Daniel one requirement. I need to see it typing and it needs to read what my agents can see. Freeze, because her sentence is this episode's whole syllabus, and here is how the exam asks its first half. A support console calls Claude on long tickets with a large output ceiling, and requests must not fail on timeouts, and agents need to see progress immediately. What should the developer do? The item parks in the corner, and by the end the console types in front of your agents and reads their screenshots, and you'll know which tickets deserve real thinking time. Call it 4 more of your 53, and the segment you started filling yesterday keeps inking today. Start with the spinner. Because it isn't a bug, It's the default shape of the call you built yesterday. Yesterday's call is one request and one response, and the response arrives all at once, only when the last token is written. A short summary hides this. A long one puts your agent in front of a blank screen for as long as the writing takes. Wait long enough, and the connection itself gives up before the answer exists, so the request dies as a timeout with nothing to show. The SDKs, the official client libraries, even check for this. Ask for a huge output without streaming, and they'll refuse the call. They know the wait can outlive the connection. The fix is streaming the same request, the same response, but the answer leaves the model as it's being written in small events over the open connection. Your agent sees the first words in a moment or two, and the timeout stops mattering because the wire never goes quiet. Same call, same price, same model. The only thing that changed is when the words arrive. The events have names and the sequence is fixed, so learn it once and you can read any stream this API will ever send you. Message start opens the response, then each content block opens, sends its deltas, the small pieces of text and closes. Message delta then carries the finishing details, the stop reason and the final counts, and message stop closes the stream. Every block carries an index, its position in the finished message, so the pieces reassemble no matter how fast they arrive. Now, the vocabulary trap, and this one's printed in the exam guide itself. The guide skill list says WebSockets, a two-way connection. The wire speaks server send events one direction from the model to you over the same HTTP call you already make. There is no WebSocket to open on this API, so an exam option that offers you one is a distractor wearing the guide's own word. One more edge the exam lies. A stream can fail after it starts, so an error can arrive as an event in the middle, long after the call itself reported success. Which means you read events, not status codes, to know a stream response finished whole. And if you want streaming safety without handling events yourself, the SDKs will run the stream for you and just hand you the finished message. Now the screenshot, and here is the part you already know without noticing. Yesterday you learned a message's content is a list of typed blocks and plain text is just the shortest kind. An image is simply another block type. The screenshot writes in the same messages list next to the words and the model reads both together. No separate endpoint and no different call. It's the request you've been building since yesterday with one more block in the list. The common image formats all work. An animation only counts by its first frame and the exact size and count limits are numbers, so they live in the cheat sheet, not in your head. What the exam cares about is the cost model. An image is built in tokens too, cut into small patches, so a bigger picture is a bigger bill, which hands you the design rule. If you already have the text, send the text, because a screenshot of a paragraph costs far more than the paragraph. Documents write the same way as their own block type, and know that a PDF is built twice over, once as its text and once as each page rendered to an image. So the desk now reads what the agent sees and the invoice tells you exactly what that convenience costs. The third piece of Priya's week, some tickets are genuinely hard and she wants real thought spent on those, not just longer answers. The models can think before they answer, working the problem through in a scratch space before the first word of the reply is written. On the newest generation, thinking is simply on, and the model decides which requests deserve it and how deep to go. One generation back, it exists but sleeps until you switch it on in the mode called adaptive, where the model still makes the depth call itself. In older code, you will meet the ancestor, a manual thinking budget set in tokens. That mode is deprecated, and the newest models reject it outright. The exam speaks tier logic here, not version trivia. Know which behavior belongs to which generation, and know the migration is removing the budget, not tuning it. Two practical ages. Thinking may not appear at all on an easy request because adaptive means the model can decide not to bother. And whether you can read the thinking text is a display option on the request itself. So when you see no reasoning, check that option before you assume there was none. The cost stays simple. Thinking is output tokens, So Priya's rule is the right one. Spend it on the hard tickets and let the easy ones stay cheap. Everything today rides on plumbing, and the exam names this plumbing directly, so give it 2 minutes and it stops being trivia. The SDKs wrap a REST API, which means plain HTTP underneath, your key in a header, JSON going in, JSON coming back. Anything that can send an HTTP request can call Claude, and the SDK is convenience and safety on top, not a requirement. Part of that safety, transient failures, dropped connections, rate limits, server errors get retried for you automatically with glowing waits between tries. When a request fails for real, the response says why as an error type your code can read, plus a request ID that support can trace. One pair is worth keeping apart. A rate limit error means your traffic spiked, an overloaded error means their load did, and only the first one is yours to fix. And when the desk needs many tickets at once, async lets one process hold many calls open in parallel. That's the live lanes answer, and the overnight batch lane from episode 1 gets its own episode later in this course. That's the technical fundamentals skill. The biggest slice of today's 4 questions, and it's the cheapest points on the paper. Just know what the wire actually is. Back to Priya's console at full size. And now you're armed. Option 1, raise the client's timeout and wait for the whole response. Option 2, open a WebSocket to the API for a two-way connection. Option 3, stream the response so it arrives as it's written. Option 4, lower the output ceiling so responses finish faster. Name the decision first. The stem is about how the answer travels, so this is a how does it call Claude question. Then find the constraint, and this stem hands it to you twice, no timeout failures, and progress visible immediately. The timeout option dies on the constraint because a longer wait still shows your agent nothing, and the SDKs won't even let that wait grow unbounded. The WebSocket option is the vocabulary trap. The guide's word offer as a connection. This API doesn't hand out and it dies on a documented fact. Lowering the ceiling, yesterday's max tokens move, is a corpse already. It cut Daniel's summary off mid-sentence yesterday, and here it would just truncate faster, so it dies twice. What survives is streaming, the mechanism built for exactly this constraint, the answer arriving as it's written over the same call. That's the pattern for every streaming question you'll meet. The constraint names the mechanism, and the vocabulary belongs to the docs, not the guide. Here's what the desk taught you today. A response arrives all at once unless you stream it, and streaming is server sent events over the same call with the first words in moments. An image is one more type block in the same list. Build in tokens like everything else, so send text when you have text. Thinking is real and costs output tokens, so spend it where Priya spends it, on the hard tickets. The counter moves to 9 of 53, and the how does it call Claude segment is most of the way inked. Tomorrow Daniel shows off the console, Priya asks him to hand it to another engineer, and it turns out the demo only runs on his laptop. Tuesday, one day after go live, and Daniel demos the console to the team, answers stream in live, screenshots get read, the hard tickets get real thought. Priya loves it, and she says the one sentence every engineer eventually hears, hand it to another engineer, you're needed elsewhere. And the handover fails in an afternoon because the console is a folder on his laptop, the setup lives in his head, and no one else has ever read the code. There's no record of what changed, so there's no earlier version to go back to, and the desk that went live on Monday can die with one laptop. Freeze because Priya's next sentence is this episode's whole syllabus. The desk can't live on one laptop. Here is how the exam asks it. A support tool built as a prototype runs only on its developer's laptop, and the team requires that any engineer can deploy it, fix it, and roll it back. What should the developer do first? The item parks in the corner, and by the end, the console lives somewhere that isn't Daniel's laptop with a history anyone can walk back. Call it 7 more of your 53, and today a new segment starts inking, the biggest one on the whole ring. Now, the surprise in the blueprint, and it's the reason this episode exists. Stack today's three skills together, and this becomes the heaviest single episode in the whole course, which is why that counter just jumped so far. And here is the trap: Claude is barely in them. Strike every Claude word out of these stems, and they'd still work on any software exam. Which is why people lose these points. They spend weeks in the API docs and donate the plain engineering questions they already half know. The three skills are just Priya's sentence asked three ways. What must the desk actually do, and where must it run? That's requirements. How does a system get from someone's laptop to a thing a team runs for years? That's the system's life cycle. And what are the working habits that turn code into a service anyone can own? That's software engineering foundations. Start where the exam starts. A business person hands you one sentence, and your job is to turn it into requirements a builder can act on. The exam's word for this skill is understanding requirements, and it names two kinds: functional and infrastructure. Both come from what the business asked for and from the solution architecture, which is just the drawing of what talks to what. Functional requirements say what the system does, summarize the ticket, stream the answer, read the screenshot. Infrastructure requirements say what it runs on, how it stays alive, and what the team must be able to do to it. So, a server that isn't a laptop, a deploy any engineer can trigger, meaning putting a new version where users run it, and a way back when a change goes wrong. Watch for of them sort. Summarize: every ticket is functional, and runs on a shared server is infrastructure. Read screenshots: functional again. And any engineer can roll back is infrastructure, because it's about what the team must be able to do to the thing. Notice the console already meets every functional requirement and fails every infrastructure one, which is the whole diagnosis of Daniel's demo in two columns. And that drawing earns its place because a requirement like rollback means nothing until you know what's deployed where. So the pattern to carry a business sentence in two lists out, and every exam stem in this skill is asking you to sort or derive one of those lists. Second skill, the system's life cycle, and the guide hands you its four verbs directly: develop, implement, operate, and maintain. Develop is building the thing, implement is putting it where users are, operate is running it day to day, and maintain is changing it safely for years. And watch that second word. The exam's implement isn't writing the code, it's standing the finished thing up where people use it. Now place the console honestly. It never left develop, because going live on Monday just meant the support team started depending on a laptop. Nobody implemented it. Nobody owns operating it, and there's no way to maintain it, and that gap is the risk Priya can feel. The frameworks the skill mentions are just named ways of walking those stages: one big pass in strict order, or small loops that visit all four again and again. The exam stays at that level, so skip the framework names and their rituals and learn the four stages themselves. Know who owns each one, and know that production credit is earned in operate and maintain, never in develop. And when a STEM names a stage, it's really asking who owns a decision, so pin the common ones down now. Who deploys is implement, who gets the call at 2 in the morning is operate, and when the thing finally gets retired is a maintain decision. Third skill, the heaviest of the three, and the guide lists its contents outright, so let's take attendance. 3. You already earned on the wire. REST APIs and JSON are how the desk has called Claude since episode 2, and async is how it holds many calls open at once. The other four are exactly what the handover was missing, so we'll install them into the story one by one. First, version control. The code moves into a shared repository, a place that remembers every change anyone has ever made to it. That's what turns rolling back into a real move, because you pick the last good version instead of reconstructing it from memory. Second, code review. Every change gets read by a second engineer before it lands, so the knowledge stops living in one head. Third, what the guide calls SDLC integration, which just means fitting your changes into the lifecycle you just made. Every change writes a fixed path, branch, then review, then test, the automatic check that nothing else broke, then deploy. So shipping stops being an event on Daniel's laptop and becomes a route that anyone on the team can drive. And fourth, refactoring, which is improving the shape of code without changing what it does, and the guide is careful to name both sizes. Small scale is renaming and tidying as you go. Large scale is restructuring the service itself, and both are only safe once the history and the tests exist to catch you. Now run Tuesday again with all three skills installed. The console lives in a shared repository with its setup scripted beside the code, so the second engineer copies it down and runs it that same afternoon. A week later, the engineer ships a fix through the same route while Daniel is on vacation, and nobody has to call him. And when that fix turns out to be wrong, the history is right there. So the rollback takes a minute and nobody's weekend is involved. The desk has finally caught up with its own users, implemented on a shared server, operated by a team, maintainable by anyone on it. These stems come in three shapes. What should you do first? Is this requirement functional or infrastructure? And which stage does this decision belong to? All three reward the same boring instinct: name the constraint, then pick the mechanism that serves it, which is episode 1's rule 1 wearing work clothes. Back to the handover question at full size, and now you are armed. Option 1: rewrite the console in a faster language so it's more reliable. Option 2: write a long setup document on the laptop so anyone can follow it. Option 3: put the code in version control with reviewed changes and a deployment lifecycle. Option 4: add the features Priya asked about first so the service is worth handing over. Name the decision first. Nothing here is about calling Claude, so this is a will it survive production question today's whole quarter in one stem. Then find the constraint, and this one is a guarantee. The team requires that any engineer can deploy, fix, and roll it back. Requires plus can is the same shape as must, so rule 2 is live and guidance is about to lose to mechanism. The rewrite dies on rule 1. The constraint is about who can operate the service, and a faster language is a generic upgrade that serves none of it. The document dies on rule 2. The first time you've needed that rule since episode 1, because a document is guidance and the stem asks for a mechanism. Writing things down isn't wrong, it just isn't what holds the guarantee up, exactly like the polite line in a prompt that was never a control. And notice it leaves the code where it was, so the one laptop is still the one laptop, now with better paperwork. Features first is a corpse already, because shipping features around process is exactly how the console became a one laptop service. So it dies twice, once on the constraint and once on the story you just watched. What survives is the boring mechanism, version control, reviewed changes, and a deployment lifecycle, which is the branch, review, test, deploy route you just built. That's the pattern for this whole quarter. When the stem promises what a team must always be able to do, guidance loses to mechanism every time. Here's what the handover taught you. A business sentence becomes two lists: what the system does and what it runs on, and you should be able to sort any requirement into one of them. A system has 4 ages: develop, implement, operate, maintain, and production credit is earned in the last 2. Version control, review, and a pipeline are what turn code into a service anyone can own, and they come before the brave changes, not after. The counter jumps to 16 of 53, the biggest single move it will ever make, and the survive segment, the largest on the ring, has started to ink. Tomorrow, Priya asks the same question in 3 places. The desk, a chat window, and a coding session, gets 3 different answers and wants to know which one is lying. The desk survived its handover, so this week the team finally trusts it and 3 people start improving the same instruction at once. Priya writes hers in a chat window, Daniel writes his in a coding session, and the service carries a third copy in its own code. They're all writing the same sentence. Never promise a refund date. On Priya's and Daniel's surfaces it holds. In the service it's buried in the message text. Instead of the field, the API reads for rules and the model promises a date. And the service is the copy that real customers actually hit. Freeze, because the difference isn't the model and it isn't the sentence, it's where the sentence was put. Here is how the exam asks it. A team prototypes a support assistant in the chat product, then ships those same instructions through the API, and the shipped version behaves differently. What best explains the change? The item parks in the corner, and by the end, you'll know exactly which surface reads your words which way. Call it 5 more of your 53, and this is the single biggest skill statement on the whole exam. So it's worth your full attention. So here are the 3 surfaces the exam names, and each one has its own answer to a simple question. Where do your instructions actually live? Start with the chat product, the one everybody prototypes in because it's the one that hides the most. The chat product already has a system prompt, meaning a standing instruction the model reads before anything you type, and Anthropic wrote it, not you. Your sentence gets layered on top of that, which is why your prototype behaves so well, and it's also why that behavior doesn't transfer. The docs say it outright. Anthropic's prompt doesn't apply to the Claude API. Your prototype was standing on a floor the API doesn't have. Now the coding surface, and this is the fact people get wrong most often, so slow down here. The instruction file you write for a coding session isn't a system prompt. Its contents arrive as a user message, part of the conversation. It works and it works well, but it lands in the same channel as everything else, meaning the same stream of messages the model reads as conversation. So later messages sit at the same level as your file and nothing in it outranks what comes after. That's a weaker promise than a standing instruction. And the API, which is where your service lives, instructions go in a field called system and it sits next to your messages, not inside them. Here is the trap, and it's a good one. No message you send can carry the role system. If an exam option offers you a message whose role is system, it's describing an API that doesn't exist and you can kill it on site. So the same sentence gets 3 different contracts, and the design skill is choosing your surface on purpose instead of inheriting one by accident. Prototype wherever you like. Just know that the thing you're shipping has to be reproved on the surface it will actually run on. That was design choice 1, where your words live. Design choice 2 keeps your desk out of the news. Which parts of a request are yours and which parts came from a stranger. Every request you build mixes both your rules, your question, and then whatever a tool dragged in, a web page, a document, a ticket, a customer type. The documented rule is structural, not clever. Third-party content goes inside tool results, which are the blocks that carry whatever a tool returned. Never paste it into your system field and never drop it into plain user text, because the model is trained to read tool results with suspicion and to read your fields as authority. And the rule runs backwards too, which is the half people miss. Do not put your own instructions inside a tool result, because that channel is the untrusted one, so your instruction may be ignored or flagged as an attack. If you need to say something after a tool runs, say it in the next turn in your own channel. There is a smaller version of the same idea inside a single prompt. Wrap each kind of content in its own label tag. That way, instructions, context, examples, and the actual input can't blur into each other. Boundaries are the whole lesson here, and the security episode later in this course is just this rule under attack. Design choice 3, and it's where the desk meets everything downstream. Prose is lovely for a human and useless to a dashboard. Priya's team wants the ticket category and the urgency in fields every time, not buried in a sentence that reads differently each run. The mechanism is structured output. You hand the model a schema, which is just a description of the shape you want, with named fields and their types. The response is then constrained to that shape. So what comes back is parsable by construction instead of parsable if you're lucky. 2 things the exam expects you to know about schemas. Not every schema feature is supported, and an unsupported one is rejected outright rather than quietly ignored. The exact list moves, so it lives in the cheat sheet. What travels is the instinct. A schema is a contract, and a contract you can't express is a design problem, not a prompt problem. The same design instinct covers the tools you hand the model, and here the docs are unusually blunt. An extremely detailed description of what a tool does, when to use it, and what its inputs mean is by far the biggest factor in whether the model uses it well. So, when a stem shows you a tool being called at the wrong time, look at its description before you look at the model. Design choice 4. The quiet one. A working session isn't a fresh start, it's a thing that accumulates. On the working surfaces, unlike the raw API, the session is kept for you. It can be resumed later, it keeps growing, and all of it keeps arriving in front of the model, which gives you 3 deliberate moves, and the exam wants you to know they are deliberate. You can clear, which starts a genuinely fresh session. You can compact, which summarizes what happened so far and carries on from the summary. And you can inspect what's currently loaded, which is how you find out that half your working space is a tool result from an hour ago. The design habit is boring and it works. One session per task, cleared between tasks, compacted when a task genuinely runs long. Context engineering gets its own episode later. For now, the exam just wants the reflex, which is that session state is something you manage, not something that manages you. Last piece of the design picture, and it's the one that scales a team: plugins. A plugin is one installable bundle that can carry skills, hooks, subagents, and tool servers at once, so a team ships a way of working rather than a folder of instructions. You add a source first, a marketplace, then install individual plugins from it, and that ordering is the whole install model. And here is the part that belongs in a design review rather than a footnote. A plugin runs code with your privileges. So installing one is a trust decision about the author, exactly like adding a dependency to your service, and the exam treats it that way, which closes the design picture. Choose your surface, mark your boundaries, name the shape you want back, keep sessions clean, and treat what you install as code you now own. Back to the prototype question at full size, and now you're armed. Option 1. The API serves a different model than the chat product, so the behavior differs. Option 2. The chat product adds its own system prompt that doesn't apply to the API. Option 3. The default temperature differs between the two, so the output drifts. Option 4. The API needs those instructions sent as a message with the system role. Name the decision first. This is about what Claude sees and says, because every option is a claim about what reached the model. There is no absolute word in this stem, so rule 2 is quiet and rule 1 does the work. Find the mechanism that actually differs between the two surfaces. The different model answer dies on rule 1. It's the generic upgrade explanation and it names nothing in the stem. Swapping models isn't what changed between a prototype and a shipped call, so it explains nothing. Temperature dies on the same rule, and that's the lesson. 2 options, 1 mistake, both reaching for a knob when the stem handed you a change of surface. And the system role option dies on the documented fact from earlier. Instructions travel in a top level field, and no message you send can carry that role. Notice how it's written to sound like the fix. It uses the right word in the wrong place, which is exactly the shape a good distractor takes. What survives is the surface answer. The chat product was adding a system prompt you never wrote, and the docs say plainly that it doesn't apply to the API. That's the pattern for this whole skill. When behavior changes and the words did not ask which surface you move to, because each one hands your words to the model differently. Here is what the 3 habits taught you. 3 surfaces, 3 contracts, layered onto Anthropic's prompt, arriving as a user message, or sitting in a top-level field on an API with no such message role at all. Untrusted content goes only in tool results, and your own instructions never do, which is one boundary rule read in both directions. Name the shape you want back with the schema, describe your tools like you mean it, and keep sessions bounded on purpose. And the refund rule ships in the services system field where the API actually reads rules. The other 2 copies were only ever rehearsal. The counter moves to 21 of 53 and the third segment starts filling. Only what runs is still untouched. Tomorrow, the three of them work in the same repository with the same instructions and still get different behavior on every run. Three engineers, one repository, and last week they agreed in a meeting on exactly how the desk should behave. So this should be the boring episode. They pull the same branch and run the same task. Each of them keeps their own copy of the agreed rules on their own machine. And they get three different behaviors. One follows the house style, one ignores it, and one stops to ask permission for every single step. Nobody broke the agreement. Nobody is doing anything wrong. The repository is identical. Freeze, because an agreement isn't a mechanism, and everything that actually decides behavior is sitting in files that nobody committed. Here is how the exam asks it. Three engineers share one repository and get different behavior. The team requires that every run use the same model version and the same project rules. What should the team do? The item parks in the corner, and by the end you'll know every file that can make two identical repositories behave differently. Call it for more of your 53, and this is the episode that turns a pile of config trivia into one picture you can hold. Before any rules, let's name the files, because every one is a real path you can go and look at. There are only two kinds of file here. Claude.md holds your written rules in plain words. Settings.json holds your switches in config. And each kind shows up in more than one place. There is a Claude.md in your home folder that applies to every project you touch. There's one committed in the repository for the team, and another can sit inside a subfolder for just that folder. Settings works the same way with one extra row. There is a settings.json committed for the team. And there's a settings.local.json that is yours alone and never gets committed. Here's the whole episode in one sentence, and everything else is just detail hanging off it. Two kinds of file in four places. The rules stack and the switches fight. Rules stacking means they all apply at once. Switches fighting means exactly one wins. Their opposite behaviors and mixing them up is where most of the confusion lives. Start with the rules, and here is the fact that fixes most of the confusion about them. Those Claude.md files don't override each other, they stack. Everything that applies gets joined into one long set of instructions, broadest first. So the organization's file leads and the folders file comes last. So your personal rule does not replace the project's rule, it sits next to it, and both are live, which has a consequence worth saying out loud. Contradictions don't resolve, they both just show up and the model has to pick. So if two engineers wrote opposing rules at different levels, nothing errors. You get a coin flip and that's your bug. Now the row for the subfolder, because it behaves differently from the other two, it doesn't load when the session starts, it loads when work actually reaches that folder. Which is why behavior can change halfway through a task with nobody touching anything and nothing in the log to explain it. One more thing about these files, and it's the one people trip on daily. Editing a Claude.md while a session is already running does nothing to that session. The contents were read once at the start, so your edit lands on the next session, not this one. Clear it, compact it, or restart, and your edit is live. That explains most of the "it ignored my rule" complaints you'll ever hear. Switch to settings.json, a different kind of file holding switches rather than sentences. Inside it you'll find keys like model and a permissions block holding default mode and deny. Learn those names because an exam question prints them rather than describing them. And these files combine the opposite way from the rules. The words stacked, the switches pick a single winner. That order is called precedence, which just means a strict ranking of who wins when two of them disagree. Top of the ladder is what your organization set, and nothing below can overrule it. Then the command line, then your local file for this project, then the project's committed file, and last your home folder defaults. Look at where the command line sits though, because it's above the project's committed file. A single run can still override a committed setting, which is why the strongest guarantees are deny rules rather than ordinary settings. There's one exception to that ladder, and the exam likes it, so slow down here. Keys that hold a list don't replace each other. They merge. A single value from a stronger file wins outright, but two lists from different files end up joined together. Which is how a list of allowed actions ends up holding entries nobody on the team remembers adding, and now the two rows that look almost identical and behave nothing alike. Settings.json is committed and shared. Settings.local.json is yours. It's git ignored and nobody else ever sees it. That local file is where your own approvals collect. Every time you click don't ask again. So it's the first thing to suspect when two machines behave differently. And a file you cannot share cannot carry a promise. Hold on to that because you are about to need it. Stay inside settings.json because one key in it decides more than the rest, and the internet will mislead you about it. The model key is how you say which version every run uses, and the question is simple. When the name you put there has no date on it, are you asking for one specific version or for whatever happens to be newest? It used to be a pointer. On older names, a name without a date resolved to whatever the newest dated version was. So the advice was always the same. Add the date, pin it down, don't let it drift under you. On the current generation, that's no longer true. A name without a date is the fixed version, and the model behind it never changes. When there is an update, it doesn't slide in underneath you. It ships under a brand new name. The documentation calls the old belief a common misconception in those exact words, which tells you the people writing exam questions know you might still carry it. So the honest answer to is this pinned is it depends which generation you are naming, and on the current one it's already pinned. Second key worth knowing by name, permissions and inside it default mode. Permission modes decide how much the tool asks you before it acts, and there's a naming trap here that the exam loves. The mode that stops and asks about everything is called manual on your screen, but its value in the file is the word default. So here is your tell. If a question prints default as a config value, it means the careful mode. If it says the default behavior, it means whatever that setup happens to start in, and those aren't the same thing. An interactive session and a scripted one start in different places, and a scripted run starts careful every time. Now the line under it, and this is the one to carry out of the whole episode. A deny rule is simply a named thing that must never run written into that list. And it blocks in every single mode, including the one that skips prompts entirely. Nothing turns it off. So if a question says a tool must never run, the answer is a deny rule, not a mode and not a polite instruction in a rules file. Back to the three engineers at full size, and now you are armed. Option 1. Agree as a team to use the same model and follow the same rules. Option 2. Commit claude.md and pin the model key in the shared settings.json. Option 3. Have each engineer set their personal settings to match. Option 4. Use a model name without a date so everyone automatically tracks the same newest version. Name the decision first. This is what Claude sees and says because every option is about what each run starts with. Then the constraint, and it's a guarantee. The team requires the same version and the same rules on every run. Agreeing as a team dies twice. It's guidance where the question asked for a mechanism. And it's the corpse from the cold open where three people already agreed and still diverged. Personal settings die for the reason I told you to hold on to. That file is git ignored, so it can't be shared. And a thing you cannot share cannot enforce a team guarantee. And the dateless name option dies on the documented fact from the middle of this episode. On the current generation, that name is a fixed snapshot, not a tracker of the newest thing. It's written to sound modern, and it describes the old behavior, which is the most dangerous distractor shape there is. What survives is the committed pair, and you can point at both rows in the tree. Claude.md in the repository and the model key pinned in the shared settings file. That's exactly what the cold open was missing. An agreement, 3 private copies, and nothing on disk that every run picks up. Here is what the 3 engineers taught you. And it's still one sentence, two kinds of file in four places, the rules stack and the switches fight. Claude.md files stack instead of overriding the subfolder, one loads late, and an edit only reaches the next session. Settings.json has a strict ladder with the organization on top, and lists merge instead of replacing. Settings.local.json is invisible to your team, so it can never carry a guarantee. The model key without a date is a fixed version on the current generation, which is the reverse of the old advice, so pin deliberately. And a deny rule blocks in every single mode, which makes it the only real guarantee in this whole episode. The counter moves to 25 of 53, which is very nearly half the exam, and you still haven't touched the what runs quarter. Tomorrow the desk is configured perfectly and starts giving answers that are polite, fluent, and completely made up. Everything is configured. The rules are committed, the version is pinned, and every engineer finally gets the same behavior. And this is the week Priya stops trusting the desk because the answers got good enough to stop reading carefully. A ticket comes back with a fluent, confident paragraph quoting a returns policy that the company has never had. Nothing crashed, no error, no warning. It reads like the best answer on the page, and it's invented. And the prompt did ask it not to. The instruction was right there, politely worded, and the model went around it. Freeze, because that sentence is the whole episode. Asking is not the same as making sure. Here is how the exam asks it. A developer needs every response to start with one specific structure. Adding instructions to the prompt works most of the time, but not always. What should the developer do? The item parks in the corner, and every move in this episode sits somewhere between asking for that structure and guaranteeing it. Call it 2 more of your 53, small on the blueprint, and it decides whether everything else you build produces answers worth shipping. Before any technique, let's look at what you are actually sending, because a prompt isn't a sentence, it's a request with places in it. There is a system field for the standing instructions, the ones that are true on every single call. There's room for examples, room for whatever document you are working on, and the actual ask. And there's the assistant's own turn, the reply, which turns out to matter more than you'd think. Now, the line that everything in this episode sits on, and I want you holding it before the first technique. At one end, you are asking the model for something, at the other, you've made it structurally impossible to get anything else. Priya's prompt was way down at the asking end. Politely worded, easy to ignore. Every move from here slides that marker, and the exam is almost always asking which end an option is at. Start at the asking end because it's still where most bad output comes from, and it's the cheapest thing to fix. Most of it traces back to a prompt that assumes something the model was never told. The docs give you a test, and it's the most useful sentence in the whole prompting guide. Show your prompt to a colleague who knows nothing about the task. If they'd be confused, so is the model. That's the check, not clever wording. Would a competent stranger know exactly what to do? And for Priya's invented policy, there's a documented move that's almost embarrassing in how simple it is. Give the model permission to not know. A prompt that says, say you don't know rather than guessing gets far fewer confident inventions because the alternative to answering stops being failure. Tighten it by making it quote the passage it used. An answer that has to cite its source is much harder to invent. That's real and it's free. But look where the marker still is. You are asking nicely, and a good prompt can still be ignored. So stop describing what you want and show it, which is the single most reliable way to steer format. The exam calls this few shot prompting, meaning a handful of worked examples sitting inside the prompt itself. Two things it tests: use several rather than one, and make them genuinely different from each other. Wrap each one in its own label tag, the angle bracket kind the docs use, so your examples can't blur into your instructions. 3 examples covering 3 different shapes of ticket teach more than 10 near identical ones. This moves the marker, and you can feel why. You've stopped explaining the shape and started demonstrating it. Here is the part almost nobody checks, and it's pure exam points. The same words perform differently depending on which slot they sit in. Who the model is being goes in the system field, the standing instruction from the last episode, what changes per request goes in the user turn. So the role and the house rules sit up top, and today's ticket sits in the message. Mixing those two is a common mistake. The second one is counterintuitive enough to be a favorite. When you are sending something long, put the long thing near the top and your question at the end. Documents first, then what you want done with them. That's the opposite of how most people draft a prompt, and one of your slots isn't in the prompt at all. A tool's description is an instruction, and it's the biggest lever on whether that tool gets used correctly. So it's part of your prompt whether you think of it that way or not. Everything so far, though, is still a request. Placed well, demonstrated well, still a request. Now, the other end of the line, and it starts with the trick everyone still recommends. Remember the assistant's own turn. For years, you could start the reply yourself, and the model would continue from where you left it. Put an open brace there, and you'd get your structure every time because the sentence was already begun. On current models, that's gone. Not discouraged, not deprecated with a warning. The request is refused. Older models still take it. From the current generation onward, it errors, and it's decided by which model you call, not by anything you switched on. So the same code that worked last year fails now purely because you moved forward. The documented replacements are two things you already met, and they are not equally strong. A schema constrains the output, so the shape is guaranteed. That's the top of the rail. A system instruction asks for the shape, which is plenty when most of the time is plenty. It sits lower, and the exam knows exactly where. That gap between them is the whole episode in one picture, and it's what the question in the corner is really testing. One thing left, and it's what separates the exam's view of prompting from the internet's. The docs don't treat a prompt as something you write, they treat it as something you measure. State what good looks like, build a way to test it, then refine against that test. Which means the answer to the prompt isn't reliable is rarely a cleverer sentence. It's a way to tell whether the next version is better. If one option offers to measure and another offers to reword, the exam wants the one that measures, and when one prompt is carrying too much, the named move is chaining, which just means splitting the work across separate calls. Draft, then review that draft against your criteria, then refine, separate calls so you can inspect each step instead of guessing. Back to the format question at full size, and now you are armed. Option 1, prefill the start of the assistant's reply so it must continue in that structure. Option 2, use structured output with the schema that defines the required shape. Option 3, move to a larger model which will follow the instruction more reliably. Option 4, reword the instruction more firmly and repeat it at the end of the prompt. The invented policy and this broken format are the same failure in different Claudes. You ask with words where you needed a mechanism. Name the decision first. This is what Claude sees and says. Then read the constraint. Every response is the constraint and works most of the time, but not always is a tell that they don't have it. So rule 2 is live and guidance loses to mechanism. Prefill dies on the documented fact you just learned. On current models, the request is refused outright, so this option describes something that no longer exists. And notice it's the most experienced sounding answer on the board. That's exactly why it's there. The bigger model dies on rule 1. It's the generic upgrade. It addresses no named constraint and more reliably is still not always. Rewarding more firmly is a corpse already. The stem told you instructions work most of the time, and the cold open showed you a polite instruction being ignored. It's the lower of the two replacements sitting right down at the asking end, and this stem asked for every response. What survives is the schema. It's the only option that makes the shape a constraint on the output rather than a request in the text. Here is what the invented policy taught you, and it's still one sentence. Asking is not the same as making sure. Be explicit enough that a stranger could follow it and give the model permission to say it doesn't know. Show examples instead of describing the shape, each in its own label tag, and make them different from each other. Role in the system field. Long documents at the top with the ask last, and a tool description is an instruction too. Prefill is refused on current models. A schema guarantees where an instruction only asks, and you find out which by measuring. The counter moves to 27 of 53, which puts you past halfway on a course where the second half is where the marks concentrate. Tomorrow, a customer conversation runs 40 messages long, and somewhere in the middle, the desk forgets the refund it already promised. A customer thread runs long. On message 6, Priya's desk promises a full refund, and everyone is happy. 34 messages later, the same customer asks when the refund lands, and the desk tells them no refund was ever agreed. Remember from episode 2 that the API forgets nothing because it remembers nothing. Every turn you resend the whole conversation. So by message 40, the request carries all 40 messages, every tool result, and the rules, and the promise from message 6 is buried somewhere in the middle of it. Freeze because nothing here is broken. This is what an unmanaged conversation does on its own. And that's the sentence for the whole episode. What reaches the model is something you design, and nobody designed this. Here's how the exam asks it. A support conversation runs long, later replies start contradicting earlier commitments, and the cost per message keeps climbing. What should the developer do? The item parks in the corner, and by the end, you'll know why a bigger window is the wrong instinct. Call it 2 more of your 53, and it's the episode that takes the C and say quarter almost all the way home. Start with the thing people get wrong about the context window, which is what the model can read in one request. Everything counts toward it. Your rules, your examples, your tool definitions, every past turn, every tool result, and the actual question. Tool definitions surprise people most. They're instructions you wrote once and now pay for on every single call. And here is the part that inverts most people's instinct. As the window fills, accuracy and recall actually get worse, which is a different complaint from slower or pricier. The documentation has a name for it. Context rot, which means a fuller window is a less reliable one, and that's a property of the model, not a bug in your code. So curating what goes in matters as much as how much room is left. What you leave out is a decision you're making, whether or not you think about it. One vocabulary note before we move on. The exam guide says context drift and the documentation says context rot. Same idea, and the docs word is the one you are more likely to see inside an answer option. And know what happens when you actually run out, because the exam splits it in two. If your input on its own is bigger than the window, the request is refused before anything runs. That one is simple and it never varies. If the input fits but the input plus the most output you allowed doesn't, today's models accept it and let generation stop partway. They tell you that's what happened in the stop reason from episode 2, so the answer arrives incomplete rather than not at all. Which explains Priya's thread exactly, and it's worth saying plainly. The promise was never deleted. It was still in the request, and in a window that full, things stop being found reliably wherever they happen to sit. So the cheapest thing you can do is take out what you've already spent. You always resend a conversation, that part is fixed. What you choose is how much of it goes back. In a long running conversation, the biggest waste is almost always old tool results, meaning what came back the last 20 times you looked something up. There is a documented mechanism for it. The API can clear old tool results once the conversation grows past a threshold you set for that, leaving a small placeholder where each one was. The detail the exam likes is that your own stored copy of the conversation isn't touched. The pruning happens to what gets sent, not to your records, so nothing is lost on your side. The docs name 4 ways to fight tool-driven bloat, and the useful thing is that they attack different sources. Load fewer tool definitions and call tools from code, letting your program run the lookup and put only what it needs into the reply. cache the part of the request that never changes so you stop paying to reread it, and prune what has already piled up. You don't pick one, you notice which of those four your particular thread is drowning in. Pruning throws away what you no longer need. The harder half is what you do still need, and that's compaction. Compaction means replacing what happened with a summary of what happened. The API can do this for you past its own threshold. It writes a summary block, and when you send that block back, everything before it is dropped from what gets sent. Again, that's the wire and not your records. Your stored conversation keeps everything. So the thread keeps going and the request stops growing, which is the whole trick. Two documented edges, because the exam likes the edges. When you have tools defined, the summarizing step sometimes calls a tool instead of writing the summary, and the summary block comes back empty. So check the block actually has content before you trust it to stand in for the conversation. And the summary is always written by the same model you are already calling, so you can't quietly hand the summarizing job to a cheaper one. There's one piece of exam bait here. An older way to do this lies in the client libraries, where the library rewrites your history itself. That one is deprecated and being removed. So an option offering it is describing the way that's being taken away, not the way forward. Both of those shrink what's already in the window. The structural move is to stop putting it there at all. If one long running job has to read a large document, search an order system, and draft a reply, all three of those can end up in the same conversation forever. The documented answer is isolation. Hand a piece of work to a separate agent that has its own window, let it do the reading in there, and take back only the conclusion. The searching, the false starts, and the raw documents never enter your main thread, and the docs frame this as a quality lever, not only a capacity one, which is worth holding on to because it's the bridge into the what runs quarter later in this course, where agents stop being a way to save room and become the thing you are designing. Back to the long conversation at full size, and now you are armed. Option 1, move to a model with a larger context window so everything fits. Option 2, compact the conversation into a summary and prune old tool results. Option 3, keep presenting the full history so nothing is ever lost. Option 4, use the client library's own history rewriting feature to shrink the messages. Name the decision first, what Claude sees and says, because every option changes what arrives in the request. Two constraints this time, and they point the same way. Answers are getting less reliable and cost is climbing. One answer has to fix both. The bigger window dies on rule 1, and this is the satisfying one because the middle of this episode disproved it directly. A bigger window doesn't stop the rot, it just delays the moment you notice, and it makes every message more expensive, not less. Resending it all unchanged is a corpse already. That's precisely what the desk was doing when it forgot the refund, so it dies on the constraint and on the story you watched. And the client library option dies on the documented fact that feature is deprecated and the supported path is the one the API runs for you. What survives is compaction plus pruning, the only supported option that shrinks what's sent while keeping what mattered. Which means it answers the reliability constraint and the cost constraint with one move. That's the whole quarter's lesson in one item. What reaches the model is a thing you design, not a thing that accumulates. Here is what the forgotten refund taught you. Everything in a request costs window, your rules, your examples, your tool definitions, every pass turn and every tool result alongside the message you are sending. More context is worse, not better, and the docs call that context rot, so curating beats capacity. Prune old tool results, compact long threads into a summary, and know the client library's own version of compaction is deprecated. And know the two overflow cases. Input alone too big is refused outright. Input plus your output ceiling stops partway with a stop reason. And when one job would fill a window on its own, give it its own window and take back only the answer. The counter moves to 29 of 53, and the see and say segment is nearly full with one piece of it left for tomorrow. Tomorrow, the desk hands the dashboard a beautiful paragraph it can't read, and when the output is garbage, you have to prove whose fault it is. The desk is answering well, so Priya's team builds a dashboard on top of it. Category, urgency, one line of summary per ticket. Daniel does it properly. He asks for a schema, the mechanism this course has recommended twice, and most tickets render perfectly. Then one panel comes up empty. The answer that fed it starts correctly and simply stops halfway through the second field with nothing closing it off. And here is the part that makes this hard: nothing failed. The call came back clean. The app can't parse half a structure, so it throws, and the code does the thing every code base does: it catches the failure and tries again. It works most days and fails often enough that nobody trusts the panel, and every failure quietly costs another call. The bill lands on Daniel at the end of the week. Freeze. Because Daniel's first question is the one this whole episode answers. Is this the model's fault or ours? Here is how the exam asks it. An integration intermittently receives responses it can't parse, and the team must be able to tell whether the model or the integration is at fault. What should the developer do? The item parks in the corner, and by the end, you will be able to point at the exact place that broke every time. Call it 3 more of your 53, and it's the episode that makes the difference between a developer who guesses and one who can prove it. Here is the whole episode in one picture, and it's the trip one ticket makes. Your code sends a request, Claude answers, your parser reads it, the dashboard draws it. A failure can only sit in 3 places along that line. It never ran, it ran and stopped early, or it finished normally and the body still wasn't something you could use. 2 of those 3 leave a mark on the response you can read. The third leaves nothing at all, which is exactly why it's the one that bites you. Start at the third place, because it's where Daniel was standing and he did the recommended thing. When something downstream needs fields, you ask for a schema. Structured output constrains the response to the shape you supply, so the shape stops being something you hope for and becomes something the request constrains. That's still right. The question this episode answers is why it wasn't enough. The exam expects you to know it comes in 2 flavors that do the same job in different places. One constrains the response body, which is what the dashboard reads, and it's the output config format field printed on screen there. The other constrains what the model puts into a tool call, which matters the moment tools arrive in a couple of episodes. Now, the part that complicates what this course told you twice already, and I'd rather complicate it than leave you overconfident. The documentation doesn't say the schema is always honored. It says compliance is guaranteed in most cases, and then it lists the exceptions. The model can refuse outright and you get a refusal instead of your fields. The answer can be cut off before the structure closes, either at the ceiling you set, or because the window itself filled and the ceiling is episode 2's trick in a new place. And when you pin a field to a fixed list of allowed values, which a schema calls an enum, one can come back in different casing than you wrote and break a strict comparison. So the habit the exam rewards is unromantic. Constrain the output and validate it anyway before you trust it. And keep 2 questions apart because they get different answers. On the exam, a schema is still the right answer when a stem asks how to guarantee a shape. This is about what your code does after the answer arrives, and there the schema makes the bad case rare without making your parser optional. Stay in the third place because there's a second way the body breaks you, and this one has nothing to do with the model at all. A structure sent in pieces arrives as fragments of text, and a fragment on its own isn't something you can parse. The place you'll actually hit this is a streamed tool call, a couple of episodes from now where the tool's input arrives exactly this way. So you collect the fragments, print it there as input JSON delta until the block stops, and parse once at the end because only the finished value is a real object. Try to parse each piece as it lands and you'll get errors that look like the model producing broken data when it's your reader being impatient. And carry the attitude from the last 2 episodes into this one. Fluent output is not verified output, and a successful call is not a correct answer. Now, the heart of the episode, and it's the picture doing the work, the same three places, each with the mark it leaves behind. The exam has two words for the ends of that line: integration layer and model layer, and for two of the three places, the response says outright which one you're in. If the request itself failed, you get an error, and that means the call didn't complete. Bad request, no permission, too many requests, their side overloaded. That's the integration layer. Something about how you called, when you called, or what was happening on their side. If the request succeeded, you get a response, and it carries a field on screen called the stop reason, which says why the model stopped writing. That's the model layer. The call worked, and this tells you what happened inside it. It finished naturally, it hit the ceiling you set, or it stopped for a reason you need to read. Which solves the cold open. The call succeeded, so the dashboard's failure was never an error at all, and no amount of retrying was going to help. Read the reason it stopped, and it says max tokens, the ceiling doing exactly what you told it to, which is one of those escape hatches, a successful call with an incomplete body, which also tells Daniel what to actually do about it, and it was never the retry, raise the ceiling, or ask for a shorter answer. And the third place is the one with no signal at all. The call worked, the model finished naturally, which the field spells and turn, and the body still isn't what your parser wants. That one is yours, and validation is the only thing that finds it. When you are standing in the first place, the shape is predictable, which is a gift for debugging. Every error the API returns comes back with a type your code can branch on, a message for a human, and an identifier for that specific request. That last one is called the request ID. It's the detail people forget and the exam likes, so log it every time. It's how anyone else can find your exact request later, and without it, a bug report is just a story. 2. You already met in episode 3, too many requests from you and their side being overloaded, which look similar and mean different things. The client libraries already retry the transient ones with weights that grow between attempts, which is what backing off means. So a retry you write yourself is usually duplicating theirs, and retrying a genuinely bad request just spends money more efficiently. Back to Daniel's question at full size, and now you're armed. Option 1. Add a retry around the parse so intermittent failures resolve themselves. Option 2. Validate every response against the schema and branch on why the model stopped, logging the request ID for that call. Option 3. Move to a larger model so the responses are better formed. Option 4. Check the HTTP status on every call, since a successful status means the response is usable. Name the decision first. This is, will it survive production? Because it's about operating the thing, not about phrasing. The stem says must, so rule 2 fires, and rule 2 says a must needs a mechanism that produces the guarantee rather than advice that hopes for it, which means the answer has to produce evidence. Fewer symptoms isn't the same thing. The retry dies twice. It's the corpse from the cold open, where retrying the same call changed nothing but the bill. And it fails the constraint outright, because a retry hides which layer broke instead of telling you. The bigger model dies on rule 1. Generic upgrade, no named mechanism, and better formed is not the same as knowing who's at fault. And the status code option dies the third way. An option can die not on either rule but on a plain documented fact. A successful status only means the call completed. The cold open's broken dashboard came from a perfectly successful call, so treating that status as proof of a usable answer is exactly the mistake being tested. What survives is the one that produces evidence, validate against the schema, branch on why the model stopped, and log the request ID so any call can be found again. Watch what those three do on the picture, because it's the whole reason this one wins. A clause for each place and nothing else on the list reaches all three. That's the pattern for every debugging item on this exam. The answer is rarely to make it fail less. It's usually to make the failure legible. Here's what the empty dashboard taught you, and it's one sentence. A failure sits in one of three places and only two of them leave a mark. Ask for a schema when something downstream has to read the answer and validate it anyway, because the guarantee is documented as most cases and not all. A streamed answer arrives as fragments, so accumulate first and parse once at the end. An error means the call didn't run and a successful response still carries the stop reason, so branch on that reason every time. Log the request ID and remember the libraries already retry the transient failures, so your own retry is usually hiding something. The counter moves to 32 of 53 and this one sat in two quarters. The stamp says survive, the ring closes C and say because output handling was its last piece. Tomorrow the desk is correct, trusted and busy and the first real invoice arrives on Priya's desk. The desk is correct, it's trusted, and that means it's busy, which is the first time any of this costs real money. Priya forwards the invoice to Daniel with one line, "This is fine if it's right, but I need to know what we're paying for." Daniel does the obvious thing first. He swaps to the cheapest model available, and the cost line drops immediately. And so does the quality. On exactly the tickets Priya cares about most, so she rejects it within a day. The cheap answer was cheap in both directions. Freeze, because the interesting question isn't which model is cheapest, it's where the money is actually going, and nobody has looked. Here's how the exam asks it. An app sends the same large policy document with every request, and cost is dominated by input. The team needs to cut that cost without changing which model they use. What should the developer do? The item parks in the corner, and by the end you'll know which lever to reach for. Plus two ways this fails silently and never says a word about it. Call it 3 more of your 53, and it's the last piece of the how does it call Claude quarter. Here is the whole episode in one picture. The request you send and the receipt that comes back with it, because Priya's invoice is just a month of these added up. Every request has a front that repeats, request after request, and a tail that changes every time, and nearly everything about cost comes down to that split. Start with the receipt's simple version because it's simpler than people fear. You pay for what goes in and you pay for what comes back. What goes in is the whole request in the order on the card, your tool definitions, then your standing instructions, then the whole conversation so far, ending in today's question. One line to carry from episode 3: when the model thinks before answering, that thinking is billed as output, even if you never display a word of it. So, on a hard ticket, you are paying for the reasoning and the reply, and both of them come out of the same ceiling, the max tokens on screen there. And a breaking change the exam will happily test. A newer model generation counts tokens differently, so the same text can come out as noticeably more tokens than it used to. Which caught Daniel out when he reran his numbers on a newer model and nothing matched the estimates he'd written months earlier. A cost model built for one generation doesn't carry to the next, so you remeasure rather than assume, and the size of the jump lives in the cheat sheet. Look at what the desk actually sends, request after request, because the waste shows up the moment you put two of them side by side. If a big chunk of every request is identical every time you are paying to read the same thing again and again, caching is what stops that. The mechanism has a shape you have to know because it's what most wrong answers get wrong. Caching caches a prefix meaning the front of the request in a fixed order, tools, then system, then messages, and those are the names printed on screen. You mark where the stable part ends with the field beside the bracket there, cache control, and everything in front of that mark gets cached. The mark has a name of its own, a breakpoint, and you are allowed more than one of them in a request. So the stable things go first, and the thing that changes goes last. Cache the front, vary the tail. Put the changing part in the middle, and everything stable that sits after it stops being cacheable. And here is the first of the two ways this fails on you without saying a word. If what you ask to cache is shorter than the model's minimum, it just doesn't cache. No error, no warning, the request runs normally and you pay full price. The only way you'd ever know is the two cache lines on the receipt, both reading 0, which is exactly where we are going next. Two more properties worth carrying. A cache entry expires, but every time it's used the clock resets, so a busy prefix stays warm on its own. And there's a longer lived option that costs more to write. The durations are numbers, so cheat sheet, but the behavior is the exam testable part. So turn the receipt over because it's where people build their dashboards, which makes it where the mistakes get baked in. In a response, it's called usage. With caching on, the input side isn't one number, it's three, and they're the three names on screen: cache read input tokens, cache creation input tokens, and input tokens. And here is the trap. The field printed there as input tokens, the one everybody reads as the input, is only that third slice. It's the leftover after the cached part, not the total. So the moment you turn caching on, that number drops sharply, while your actual input hasn't changed at all. A team watching it reads a far bigger saving than they actually got, and a team modeling cost from it undercounts every request. Your true input is all three added together. The cached part still costs you something, just much less, and writing it in costs a little more the first time. That's silent failure too. The first one quietly costs you money, and this one quietly costs you the truth about it. Token tracking isn't hard, it's just very easy to do against the wrong field. If a STEM describes a cost report that stopped matching the invoice, this is the first thing to suspect. Back to Daniel's first instinct, and let's give it a fair hearing because model choice is a real lever. The exam wants tier logic, not a memorized lineup. There is a top tier for the hardest work and a middle tier that's the workhorse at scale. And there's a fast, cheap tier for high volume and simple tasks, which is the one Daniel reached for. Names and prices change every few months. The roles are what's stable, and that's what a STEM is testing. But here is the sentence from the docs that Daniel needed, and it's quotable. Tuning effort is often a better lever than switching models. Effort is how hard you ask it to think before answering, which is the thinking from episode 3 seen as a dial rather than a switch. So you turn that down on the easy tickets before you downgrade every ticket to a weaker model. That's what went wrong in the cold open. He swapped the model for every ticket when he could have turned the dial down on the easy ones instead. Watch which side of the receipt that moves, though. Effort is an output lever, so it does nothing for a bill dominated by the same document going in every time. One last tool, and it closes the loop between guessing and knowing. There's an endpoint that counts the tokens in a request before you send it. Count tokens on screen there, and it generates no answer and costs nothing, which turns cost from something you discover on an invoice into something you can check in a test. And that's the difference between a cost model and a hope. Back to the policy document at full size, and now you are armed. Option 1, switch to the cheapest available model to reduce the per token price. Option 2, cache the policy document as a stable prefix, so it isn't reread on every request. Option 3, lower the output ceiling so responses are shorter. Option 4, mark each ticket's text for caching since the tickets are what change. Name the decision first. This is how does it call Claude because every option changes the shape or the cost of the call. Then read both constraints. Cost is dominated by input and the model is fixed. Hold those two while the options go down. The cheapest model dies twice and both deaths are ones you already know. It's a generic knob under rule 1 and the stem forbids changing the model at all. It's also the corpse from the cold open, where it cost Priya exactly the quality she needed. The output ceiling dies on rule 1. It's a generic knob and it's on the wrong axis entirely because the stem told you the cost is dominated by input. And caching the ticket text dies on the documented fact from the middle of this episode. Caching caches a stable prefix and the tickets are the part that changes every time. It's the most plausible sounding wrong answer here because it names the mechanism correctly and points it at exactly the wrong end of the request. What survives is caching the document, the one stable thing in every request, which is precisely what the mechanism is built for. That's the pattern for cost items. Find what repeats and stop paying for it twice before you go looking for a cheaper model. Here's what the invoice taught you, and it's one sentence. Every request is a front that repeats and a tail that changes, and the receipt says which one you are paying for. You pay for everything going in and everything coming back. Thinking is billed as output even unseen, and token counts shift between generations. The field called input tokens is only the uncached leftover, so true input is all three parts added together. Caching caches a stable prefix, so stable things go first and the changing part goes last, and below the minimum it silently does nothing. Tune effort before you switch models and count tokens before you send rather than after you are billed. The counter moves to 35 of 53, and the how does it call Claude segment is one sliver short of full. Tomorrow closes it. Tomorrow, Priya wants 10,000 tickets analyzed by morning, and the overnight lane you parked in episode 1 finally gets its answer. Priya wants every ticket from the last 3 months read and categorized all at once as a one off. 10,000 of them, and she says the part that matters. Nobody needs these tonight. I want them by morning. Daniel does what looks fastest and sends all 10,000 as ordinary live calls fired off at once. The API caps how fast anyone can send, so it starts refusing them, and that's what rate limited means. Sending crawls, he pays full price for everyone, and at 9 the next morning the job is still going. He optimized for speed and missed the only deadline that existed. Freeze because Daniel answered the wrong question. He asked how to go faster when the question was which lane this work is in. Here is how the exam asks it, and this one is close to a question the exam guide prints itself. A developer must process 10,000 tickets overnight for a non-urgent report, and cost is the primary concern. The results aren't needed until the following morning, which approach best fits. The item parks in the corner, and by the end you'll pick the lane and know it's two silent failures. Call it one more of your 53, and this is the piece that finally closes the how does it call Claude quarter. Here is the whole episode in one picture, and it's a fork in the road with two lanes running out of it. The exam treats them as two designs, and choosing between them is part of the job. The top lane is the one you've used in every episode so far, with somebody waiting at a screen. The bottom lane is for work where nobody is waiting, and the docs say exactly that. It suits tasks that don't need an immediate response. You hand over a pile of requests and come back for the results later, which is why it's drawn long. What you get for giving up the wait is the price tag now hanging on that lane, less per request and far more of them moving at once. The discount and the window are numbers, so they are in the cheat sheet. The trade is the testable part, which gives you one question that resolves almost every stem in this area, and it's written on the fork. Does somebody need this answer right now? If yes, it's the top lane. If no, it's the bottom one. Stems rarely say lane, so learn the pair they do use. Synchronous on top means you wait on the answer. Asynchronous underneath means you hand the work over and come back for it later. Notice that neither the model nor the prompt changed. What changed is the lane. Everything left in this episode happens inside the bottom lane, so the top one dims now and stays there. Zoom into the mouth of that lane, because what goes in is one envelope carrying many requests. Each request inside looks like the ordinary call you already know, and the whole thing is called the Message Batches API. Every card also goes in wearing a tag you write yourself, and that tag is the thread of this episode. There is a ceiling on how many requests fit and one on the envelope size, and hitting either one stops you at the door. A few parameters can't come along, and the one you already know is on the card there, the stream flag. Streaming exists so a person can watch an answer arrive, and in this lane nobody is watching. If a stem asks for live token by token output, that stem has just ruled this lane out for you. The envelope sets off down the lane, and while it travels, it carries a status you can check. That's the field on screen there called the processing status, and it moves from in progress to ended. You poll it, which just means asking for that status now and again instead of holding a connection open. Ended means finished, not succeeded. Each request inside still carries its own outcome. It works through the pile inside a window, and anything unprocessed when that window closes comes back marked expired. That window is the outer limit, not the normal wait. Most finish well inside it, so an overnight job lands by morning. Inside the lane, the requests run concurrently and in any order, which is how the pile moves so fast. Episode 10's prompt caching still works down here, but only on a best effort basis, and the any order fact is why. Nothing guarantees the part you cached is still cached at the moment any particular request runs. The envelope reaches the far end and the rows come out into a results file you download. Once the status says ended, the batch hands you an address for that file, printed there as the results URL. It's a .jsonl file, one result per line, and you read it a row at a time. The rows can come back in any order, and the docs say it flatly. The order may not match the order you created the batch in. So the results file is not your input file with the answers filled in, it's the same set of answers, shuffled. Look at the threads on the picture. They cross because where a row lands has nothing to do with where it started. Call that silent failure 1, and here is the trap. Nothing tells you. Walking both lists together, row by row, cuts the threads and reties them to whatever is sitting at that position. Every row has a plausible answer. The file is the right length, and ticket after ticket carries somebody else's analysis. Nothing errors, so if an option offers to match results to inputs by position, that's the trap wearing tidy clothes. The fix is the tag you tied on at the mouth, and it has a name, the field on screen there called the custom ID. It's your own label for that request, it goes in with it, and it comes back on the row. So the ticket number goes in, and you look the answer up by ticket number on the way out, never by position. Each row carries its own outcome, succeeded, errored, cancelled, or expired. You are only billed for the ones that produced an answer, so the rest cost nothing. Silent failure 2 is hiding in that error pile, and you can follow its thread back to the mouth. The envelope size is checked when you hand it over, but what's inside each request is checked later inside the batch. So a malformed request doesn't bounce back. It sits there quietly until everything else finishes, which can be a long wait. Which is the argument for testing one request in the top lane before you send 10,000 down this one. Everything so far assume this lane exists wherever you are deploying, and that catches people in production. Teams often buy the same model through the cloud platform they already have a contract with. Those platforms aren't guaranteed to carry every feature of the first-party API, and on at least one of them, this bottom lane was never built. A request that asks for a missing feature is refused at the door rather than quietly degraded. So before you design around a feature, check that the platform you are deploying on actually has it. Which platform lacks what keeps changing? So that's cheat sheet material. Back to Priya's 10,000 tickets at full size with 4 options under it. Option 1. Send every request synchronously through the Messages API in parallel. Option 2. Hand all 10,000 to the Message Batches API as one submission. Option 3. Keep the synchronous calls and lower max tokens on every one of them. Option 4. Keep the synchronous calls and switch to the smallest model available. Name the decision first. This is how does it called Claude, because every option is about the shape of the call. Then read the 2 constraints the stem handed you. Nobody needs the results until morning, and cost is the main concern. Both of those are already on the picture. The fork asks who's waiting, and the price tag has hung on the bottom lane since we drew it. And keep rule 1 from episode 1 in reach. When a stem names a constraint, the answer is the mechanism built for it. A generic knob, like a smaller model or a lower ceiling, is a distractor. Option 1 dies twice, and you watched both. It never leaves the top lane, so it never gets that lower price. And firing everything at once is what got Daniel rate limited and left the job still running at 9. The output ceiling dies on rule 1. Max tokens is a knob on the top lane aimed at how long one answer is allowed to be. Set it loosely and nothing changes. Set it tightly and you've cut off the analysis you asked for. The smallest model dies on rule 1 as well, which is why that chip looks familiar. Same move as option 3. Reach for a knob on the lane you are already in. Two options dying on the same rule is the shape of the question, and the picture shows you why. 3 of the 4 never leave the top lane. They reach for a knob when the stem handed you a change of lane. What survives is the one that moves the work down into the lane built for exactly this kind of pile. Read the stem for who's waiting, and if the honest answer is nobody, you've already picked the lane. Here's the whole episode in one sentence. 2 lanes, and the question that picks one is whether anybody is waiting. Take the bottom one and you give up the order you send things in, so you name every request on the way in. A batch is one envelope of many requests with a ceiling and a window. Stream can't come along and you poll its status. The rows come back in any order, so you follow the tag you tied on, the custom ID, and never the row number. A malformed request stays quiet until the whole batch ends, so test one in the top lane first. And the same model bought through another cloud platform isn't guaranteed to have this lane, so check parity first. Two things move at the close, so take them separately. The counter goes up by 1 to 36 of 53. The segment is the other one, and this was the last episode carrying that decision, so its ring inks full. You can build a call, watch it stream, price it, and queue 10,000 of it. Tomorrow, a customer asks where their order is, and the desk gives a beautifully written answer that it had no way of knowing. A customer asks the simplest question a support desk ever gets: where's my order? The desk is the app answering these tickets, and it invents a shipping date because nobody gave it a way to look. So Daniel, the engineer who owns the desk, wires up a lookup and spends the afternoon on the function which works in his desk. Then the desk calls it with the customer's name where the order number goes, and on the next ticket it doesn't call it at all. So he does what everyone does next and adds a line to the instructions telling it to always check the order system. Nothing changes, same wrong argument, same skipped calls, and now a line that makes it look handled. Freeze, because it works when Daniel calls it and fails when Claude calls it, so the fault sits between those two calls. Here's how the exam asks it. An app gives Claude a lookup tool that works when called directly, and Claude calls it inconsistently with a wrong argument. What should the developer do? The item parks in the corner, and you'll answer it yourself by the end. Call it 2 more of the 53 questions you'll sit, and it opens the last of the 4 quarters, what actually runs. Here is the whole episode in one picture, a loop the desk goes round whenever it needs a fact it hasn't got. Daniel's tool card slides into the first step. You send your tools and the ticket, Claude asks for one, you run it, you send the result back. 3 of those 4 steps are your code. Claude never runs your function and never touches your database. Its only move is the second step, choosing a tool and filling in its arguments, and it plays that move from what you wrote. So hold on to this. You own 3 steps, Claude owns 1, and what goes wrong in the model's hands went wrong in something you wrote. The loop's only branch sits on Claude's step in the field on screen called the stop reason, which an option list prints rather than describes. Tool use means it wants a tool, and what comes back is a tool use block carrying the tool's name and an input field with the arguments. End turn means it's finished and you have your answer. Don't code a 2-value world though. The other stop reasons on screen, like running out of room, leave the loop too. The exam guide calls this the agentic harness, and a while loop around one request is all it is. Stay on the third step, because whose computer runs the code splits tools into 3 buckets, and that's what a stem turns on. Tools you define run on yours, and so do Anthropic's own definitions for common jobs, printed as bash and text editor. Both are client tools. Prefer one of Anthropic's to your own equivalent because the model trained on those exact signatures and calls them more reliably. Server tools are the third bucket, like the web search, which runs on Anthropic's side, so the result arrives in the same reply and you build no result block. Back to the first step and to the question that changes how you build these. What actually crosses from your step into Claudes, not your function and not Daniel's afternoon of work on it. Three fields cross, the three on screen, the name, the description, and the input schema, which is the shape of the arguments. Of those three, the description is the only one you write in sentences, so it carries what a name and a shape can't say. The docs are unusually blunt about it. A detailed description is by far the most important factor in tool performance. So stop writing it as documentation for the next engineer. It's the interface, and step 2 has nothing else to read about what it's for. Which reframes Daniel's afternoon. A perfect function and a forward description. So the field that mattered said almost nothing. A good one covers 4 things, and the docs ask for at least 3 or 4 sentences, more than anyone writes by instinct. What the tool does, when to use it, and when not to, what each parameter means in plain words, and what it can't do. The when to use half tells the model an order question is this tool's job, and without it you get Daniel's skipped calls. The when not to half runs the other way, stopping a tool firing on every ticket regardless. Drop one field to the input schema, and Daniel's wrong argument is the same bug in different clothes. He named a parameter and never said what it was, so the model guessed a customer's name, identifies an order, and nothing said otherwise. Two switches sit beside those fields, and neither one writes your description for you. Strict true printed there forces the arguments into the shape you define, and it's the answer when a stem says inputs must conform. Tool choice set on the request forces the call itself, so it's the answer when a stem says a tool must run every time. Both guarantee mechanics, neither tells the model what your tool is for or which ticket it belongs on. Pull the zoom back out to the whole set in that first step, because the exam asks about the set as much as one tool. The instinct is one tool per action. The guidance is the opposite. Fewer, bigger tools with the operations behind one parameter the docs call action. Choosing between 8 near identical names makes more mistakes than choosing an action on one clear tool. Once a tool is that big, its name has to say which system it belongs to, which is namespacing. The lookup becomes orders get order, the system in front of the verb, because the return system is next door and a bare name fits both. One decision in that set reaches round to the fourth step, and it's what your tool hands back. Returning the whole record because choosing his work feels harmless, and it's episode 8's window stuffing problem again. Return the fields that answer the question. Status, date, item, and stop. That arc lands you on the fourth step, which has rules, and breaking one gets the request rejected rather than answered badly. The result goes back as a tool result block printed there in the very next user message straight after the request it answers and before any text. Its tool use ID pairs it with that request, and a call that works alone but comes back rejected is usually this ordering. When the tool fails, you don't crash and you don't hide it. The failure goes back flagged with the is error field, and Claude works with it. The wording matters because the model reads it the way it reads everything else. The doc's advice is to say what went wrong and what to try next instead of an error that just says failed. When it asks for two things at once, the fourth step still happens once, and every request gets a result in the same message. Split them into separate messages and you lose the parallel calls because the history you send is the pattern it copies. The gate on the arrow from Claude's step into yours is where you decide which tools run unattended. A lookup can just go, a refund asks a person first, and that's an approval pattern, your loops call and not the models. Back to the inconsistent lookup at full size. Option 1. Set strict true on the tool so its inputs are guaranteed to match your schema. Option 2. Expand the tool's description to say when it applies and what each argument means. Option 3. Add a line to the system prompt telling the model to always check the order system. Option 4. Lower the temperature on the request so the model behaves more predictably. Name the decision. This is what runs the tool as a thing the model chooses and calls. Then read the giveaway. The tool works when called directly, so the running of it is fine and the fault is what it was told. Option 3 dies twice and you watched it die. Daniel added exactly that line and nothing changed. Put it on the picture and it sits outside the loop. A general instruction far from the tool that has a field for this. And forcing the call is what tool choice is for, which still wouldn't fix a wrong argument. Option 1 is the good distractor because it points a real mechanism at a real sounding symptom. Strict sits on the first step with the definition, guaranteeing the arguments arrive in the shape you defined. It can't tell the model that an order is identified by a number and not a name, and it says nothing about whether the tool is called. That's the fact from the middle of this episode. Shape and meaning are different problems, and this one only touches shape. The temperature dies on rule 1, the archetypal generic knob, and it touches no step of the loop you own. Inconsistent is a variability shaped word, so the eye goes to the sampling dial when the cause was a thin description. What survives is the description, the one field of the three that says what a tool is for and which ticket it belongs on. That's the pattern for tool items. When a tool works alone and fails in the model's hands, the fix is in what you told the model. Here is the missing order in one sentence. You own 3 steps of that loop, Claude owns 1, and it plays its step from what you wrote. Claude never runs your code, and which of the 3 buckets a tool sits in decides what your app owes it. The branch is on the stop reason, where tool use goes round again and end turn is your answer. Step 1. Hands over a name, a description and an input schema, and strict true forces the shape, never the meaning. A description says what the tool does, when it applies, when not to, what each parameter means and what it can't do. Build fewer and more capable tools, prefix them with their system, and return the fields that answer the question. Step 4 goes back in the next user message before any text, failures come back flagged, and a consequential tool asks first. The counter moves to 38 of 53, and the what runs quarter has its first piece. Tomorrow the returns team asks for the same lookup in their app, and copying the code into a second place is how this stops working. The order lookup works and word gets around, returns wants it, and so does the shipping dashboard. Daniel does the fastest thing going. He copies the tool into the returns app and it works by lunchtime. Then the order system changes shape. The desk's copy gets fixed and the returns copy doesn't because nobody remembers it exists. So a customer gets told 2 different things about one order depending which team picked up the ticket. Freeze. Copying it looked like reuse, right up until the copies stopped agreeing. Copy a capability and you've got 2 to keep in step. And that's the problem this episode is about. Here is how the exam asks it, close to one of the guide's printed samples. A team needs Claude to reach an internal inventory service over its REST API, reusable across several applications and maintained separately. Which approach best fits? The item parks in the corner, and by the end you'll have 4 places to put a capability and know which wins. Call it 3 more of your 53, one of the bigger stops left. The alternative to a copy is one program everybody connects to over a protocol called MCP, Model Context Protocol. That program is an MCP server. It runs on its own and offers its capabilities over one agreed interface so any app can use them. One host at this end, one server at that end, one wire between them, and the rest of the episode lives on this drawing. Build the lookup once and returns runs its own wire to it, and those 3 empty slots are the first thing to settle. Start at the host end because stems describe this shape in words and never draw it. The host is the app the person is using, and it makes one client for every server it wants to talk to. Each client talks to exactly one server, so 5 servers means 5 clients in one host, never one juggling 5. Now the far end, where two limits are built in on purpose. A server can't read the whole conversation or see into another server. It gets its own calls arguments and nothing else. So the wire is a boundary as well as a connection, and episode 16 picks that up. Returns has its wire, so what do they get to reach down it? Not a bag of tools. 3 slots hang off the far end, and the spec calls them primitives, the word a stem uses, so take it. Tools are executable actions, resources are data, the server hands over when the app asks, and prompts are ready-made templates. Now the part the exam is built to catch. A different party controls each slot, and only one is the model. Tools are model controlled, so the model decides when to call one, and the desk's lookup is one. Resources are application controlled, so the returns app pulls in the refund policy itself and the model never reaches for it. Prompts are user controlled, so a person on the desk picks a refund reply draft of a menu, usually a slash command. 3 slots, 3 different hands, and 1 wire, they all arrive down. So a stem asking which primitive is application controlled has one answer, resources, and bag of tools costs marks. So authoring a server is declaring what goes in each slot and the shape of its arguments. Returns runs on the desk's machine, but the dashboard team is in another building, and that decides the transport what the wire is made of. There are 2, and the first is STDO, named after the standard input and output streams every program is born with. The client launches the server as a child process, and they talk over those streams, one message per line. The second is streamable HTTP, for a server running somewhere else, where the client posts to one address and gets its reply. STIO when the server sits on your machine, streamable HTTP when the dashboard team has to reach it from theirs. One rule inside STIO has broken more for servers than anything else here. Standard out carries valid MCP messages and nothing else. So a stray debug line, there is a corrupt message and the wire breaks. Logging goes to standard error, the second stream on screen, which exists for that. If a stem says sockets, read it as a custom transport reusing STDO's framing, not a third one. Once the wire crosses machines, the server has to be hosted where other teams can reach it and check who's plugging in. Back at the host end, a stem gets concrete because the transport you picked is written in a file. A project's servers are entries in the file on screen, .mcp.json, checked in so returns gets the same wire without retyping it. You add an entry with the command beside it, Claude MCP add, and the transport you pass becomes the type field in it. The order system changed shape once already, and this time both ends check first in an exchange named on screen. Initialize. The client names the version it speaks, the server answers with the one it'll use, both list what they support, and a mismatch fails here. In the revision most tools pin, it also opens a session carried in a header named MCP session ID. One aside boxed off, the only place in this course where the ground moves under you. The newer revision drops the handshake and the session, so every request carries its own version instead. The server accepts or rejects each one on its own. So take the safer habit, don't assume a server remembers you and pass the ticket ID every call instead. Call this the 4-way call. Every option in the worked item is a place on this one wire. Built-in tools ship with the host, covering file work, search and running things, and often that's the whole answer. A custom tool sits inside one host with no wire leaving it, which is what episode 12 built and what Daniel copied. An MCP server sits at the far end, the only one of these that several hosts can reach at once. The fourth doesn't sit on the wire at all, and people reach for it when what they actually need is the third. Take the docs framing. MCP connects Claude to a service, and a skill teaches it how to use that service well. There are layers. The server is the wire. And the skill is what the host knows about using what's on the end of it. A skill is a folder holding a file called scale.md, and its description is what decides whether it ever fires. So the sorting question is short: does it need to do something new or to know something? Doing means a tool, and a tool several applications need means a server at the far end of a wire. Knowing means a skill, and check what already ships before you build any of them. Back to the inventory service, which is the desk's problem with a different name on it. Option 1: copy the inventory logic into each application that needs it. Option 2: build an MCP server that exposes the inventory operations as tools. Option 3: write a skill that documents how to call the inventory service. Option 4: use a built-in tool, since built-ins can reach any internal service. Name the decision what runs, because every option puts the capability somewhere different. Then read the two constraints, several applications and maintained apart, since rule 1 says the answer is the mechanism that constraint asks for. Option 1 dies twice and you watched both deaths. It's the copying that started this episode. Every copy is maintained by whoever owns that app. The opposite of independently, and copies that drift stop being one capability. The skill dies on rule 1, and the constraint it fails is the one about several applications using the capability. A skill is knowledge, and knowing how to call a service leaves the returns app with nothing to call. The built-in dies on a plain fact. Built-ins do a fixed set of things, and reaching your internal service isn't one. Watch that shape, an option that explains itself with a fact that isn't true. What survives is the server, one implementation at the far end of one wire, and every other option leaves it inside a host. The operations go in the tools slot, the model controlled one, so the model calls them and both apps get one answer. When a stem says several applications and independently maintained, it has described the far end of a wire. Daniel deletes his copy, returns runs the wire instead, and one customer gets one answer, a copy makes two, a wire makes one. The far end has three slots with three controllers: tools the model calls, resources your app pulls in, prompts a person picks. The host makes one client per server, and a server can't read the conversation or see other servers. The wire is STO on one machine or streamable HTTP across machines with nothing but MCP messages on standard out. Check which revision a server's docs are written against, since the newer one drops the handshake and the session. And 4 places for a capability picked by one question: does it need to do something new or to know something? The counter moves to 41 of 53, and the what runs quarter is about half inked. Tomorrow the triage script that picks which tool to call has 40 branches, and Daniel wants to add the 41st. The desk decides which tool to reach for using a script Daniel wrote, a dozen categories, 40 branches deep. Priya asks for a 13th category, and Daniel can't add it without risking the other 40 branches. So he proposes the fashionable fix: rip out the branches and let an agent work it out. And Priya asks the question that decides this episode: if it chooses for itself, how do I explain what it did? Freeze. Daniel's diagnosis is right and so is Priya's worry, so the answer has to satisfy both. Here is how the exam asks it. A desk sorts tickets into a dozen categories, each needing its own handling. The logic is a long chain of handwritten conditionals that's hard to extend. New categories arrive often, and the support leads have to explain why a ticket went where it did. Which approach best fits? The item parks in the corner, and the exam has a vocabulary for this argument. Call it 4 more of your 53, and every stop left is worth another 4. Here's the whole episode in one picture, one line you read, left to right. 3 positions, and the bracket over the last 2 is agentic systems, which covers both things they're arguing about. Daniel's chain slides into the left panel, because a workflow is the model and the tools running through paths you wrote. In an agent, on the right, The model directs its own process and tool use and keeps control of how it does the task. That's the whole distinction, and it turns on who picks the next step. The first position is Anthropy's online. Find the simplest solution possible and only add complexity when needed, which includes nothing agentic at all because for plenty of jobs, one good call with examples is enough. The captions are the decision rule. Workflows give predictability and consistency on well defined tasks. Agents are better where you need flexibility and model driven decisions at scale. Every move right buys one and spends the other, trading latency and cost for performance, so move right only when the one before won't do. Priya still has to read back why a ticket went where it did, so the fix stays in the left panel where a workflow takes 5 named shapes. Prompt chaining is a fixed sequence where each step works on the output of the one before, with an optional check between steps. That check is a gate code rather than another model call, deciding whether the chain carries on. It trades a little latency for accuracy by making each step an easier job. Routing reads the input, works out what kind it is, and hands it to the branch built for that kind. The payoff is separation of concerns. Each branch gets its own prompt, not one prompt good at everything. Parallelization runs calls at the same time and combines results in code in two flavors. One flavor breaks a task into independent pieces run together. The other runs the same task several times for a spread. Orchestrator workers has a central model break the task up, hand pieces to workers, and stitch them back. The difference from parallelization is the testable one. The subtasks aren't decided in advance, they're worked out from the input. Evaluator Optimizer runs two calls in a loop, one producing an answer and one grading it with what to fix. It earns its keep when you have clear criteria for good, like the desk's tone guide, and another pass measurably improves things. Two of those let a model decide at runtime. Orchestrator workers picks the pieces, evaluator optimizer picks when to stop looping. Both are still workflows. The model picks what the work is, your code picks where it goes, and where it goes is the next step. Daniel wanted to hand the whole desk to an agent, so cross the bracket. What he was proposing is smaller than the word suggests. An agent is a model using tools in a loop, deciding what to do next from what came back last time. It's episode 12's loop, keyed on the field on screen. The stop reason, tool use means go round again, and turn means no tool call came back and the loop is done. What changed is who picks the next step. Here, the model does, not your code. The fit test is about your problem, not the technology. If code you wrote picks the next step, you are on the left. If you can't predict how many steps it takes or hard code a path, that's the right panel earning its place, and a ticket isn't that. The bill is real, higher cost and errors that compound because a wrong step early feeds every step after, which is Priya's worry stated honestly, and why the docs ask you to show the planning steps, not only the answer. Daniel's next idea is everyone's one agent per category, and you don't get a new picture, you get this panel copied. The exams published skill list names this manager and supervisor hierarchies, word for word. Manager, supervisor, and lead agent are three names for one role, so a STEM can't lose you with another. The name printed there is orchestrator subagent, a lead agent spawning and managing specialized subagents. The fourth name is orchestrator, and it's a trap because it also names a workflow back on the left. Here is the collision, settled by the same question as everything else. The workflow card on the left hands subtasks to worker calls, and your code decides what runs next. The multi-agent one hands work to whole agents, each picking its own next step with its own tools and context. Pull one subagent forward because the isolation is what lets Priya be told what it was asked and what it answered. It gets its own context window, its own instructions, tools, and permissions. Only the prompt you hand it crosses on the way in, so anything it needs goes in there. Only its final message comes back, so the middle stays inside it and the parent's context stays clean. What never crosses is the parent's conversation, its tool results, and its system prompt. The project instruction file does cross claude.md and Claude code passes it down by default. An SDK app passes it only when setting sources includes the project settings, and that's the tested qualifier. Here is the beat this episode exists for, and it runs against everything you'll read this year. The guidance is to start with one agent because more usually isn't better. Several agents reliably beat one in exactly three situations worth memorizing. The first is context pollution, when a context fills with material that drags the work down, and the fresh window you saw is the cure. The second is work that genuinely runs in parallel, and the third is specialists picking tools better. The premium is always there. Inside those three, you get something for it, and Daniel's 12 agents aren't in any of them. And the line worth keeping. Teams who built elaborate multi-agent systems often got there with better prompting on one. Whatever replaces Daniel's chain, he isn't writing the loop himself, and the blueprint names three things he'd build it on. Lang graph is a graph you draw for long-running stateful agents, mixing hard-coded steps with model-decided ones. Strands agents is AWS is open source kit, model-driven, shipping ready-made multi-agent patterns. Pydantic AI is a typed agent loop whose output is validated against a schema you declare. The strip spans both panels, and none of the three changes which side you are on. Back to Daniel's 40 branches. Option 1. Rip out the conditionals and let an autonomous agent pick its own steps per ticket. Option 2. A routing workflow, one classifier in front and one prompt per category. Option 3. A larger model handling all 12 categories in one carefully written prompt. Option 4. Parallelization, running all 12 handlers and picking the best output. Name the decision, what runs, then work the options one at a time against the picture on screen. Option 1 dies twice, both on screen. It's Daniel's proposal from the cold open, and Priya killed it in the next breath. It's the one move across the bracket, and a worn out chain isn't proof the whole left side failed. Sorting a ticket into one of a dozen known categories is a well-defined task, and the stem wants a reason you can read back. The bigger model dies on rule 1, the constraint rule. The answer is the mechanism built for the stem's constraint, not a knob. One big prompt is the card outside the bracket, and the desk outgrew it at 40 branches. Running everything in parallel dies on a documented fact, and it's the good distractor because it's a real pattern. Parallelization is independent pieces run together or the same job repeated for a spread, and neither is sorting one ticket to one specialist. What survives is routing named for this exact shape. Classify, then hand off to something specialized still inside the left panel. And notice what it gives Priya, because this is the cold open's actual fix. Adding a category means adding one branch with its own prompt, and it can't break the other 12 because nothing was wired to it. That's what separation of concerns buys. 40 coupled conditions became 12 independent ones behind a classifier you can read. What the 13th category taught you is one sentence: who picks the next step decides which side of the bracket you are on. A workflow runs the paths you wrote. An agent directs its own process. Several agents is orchestrator, subagent, and it's all agentic systems. 5 named workflows on the left: prompt chaining, routing, parallelization as sectioning or voting, orchestrator workers, and evaluator optimizer. On the right, a model in a tool loop that ends when it answers with no tool call, earning its cost only when you can't predict the steps. Start with the simplest thing that works, and with one agent, several win only on context pollution, real parallelism, or better tool picking. The counter moves to 45 of 53, and what runs is one sliver short. Then you decide to build the thing and find out that the loop is the easy part. Episode 14 ended with one genuinely open-ended job on the desk, so Daniel builds the agent, and the loop takes him an afternoon. Call the model, run the tool it asks for, hand back the result, go round again. It works on the first ticket. Then it needs to read files, run commands without running the wrong one, remember last week, and pick up after a crash. 3 weeks later, the loop is still the smallest file in the project, and none of what surrounds it is what he set out to build. And Priya adds the requirement that changes the shape of the problem. It must never delete anything without asking her first. Never, not usually. Freeze. Daniel didn't underestimate the loop, he underestimated everything that isn't the loop. And that thing has a name. Here is how the exam asks it. A team has a working custom tool loop, and the agent now needs file access, shell execution, and memory across sessions. It must never run a destructive command without an explicit check, and the team wants to minimize what they build and maintain themselves. Which approach best fits? The item parks in the corner, and we come back to it once you can see what Daniel was really building. Call it 4 more of the 53 questions you'll sit, and it closes the what runs quarter. Here is the whole episode in one picture, and the cold open drew half of it. The loop is that small circle in the middle, and everything Daniel spent 3 weeks on closes into a ring around it. A harness is the tools, the context management, and the execution environment that turn a model into an agent that can do things. Those 3 bands are the ring, and the loop is one item inside them, not the thing itself. So here is the episode in one sentence. The loop is the middle, the harness is the ring, and you choose who owns the ring and where it sits. The clearest example is one you probably used. Claude Code is the ring, and Claude is the model in the middle, which is why 2 products running the same model behave nothing alike. The ring differs, not the middle. Light up the middle because the loop has a shape worth knowing. Gather context, take action, verify the result, and go again until it's done. One full trip round is a turn, so you count turns by trips, and the loop ends when Claude answers without asking for a tool. 3 ways to build one, and they're a ladder, so watch how far the shading reaches up it. At the bottom, you write the loop yourself on the messages API. Nothing is filled in, and this rung is where Daniel has been for 3 weeks. In the middle sits the Claude Agent SDK, a library that runs the whole ring inside your own process. You call the entry point printed there query, and it runs on your own machine, not on Anthropic's. At the top, the hosted product, Anthropic calls managed agents, where they run the ring and the plate under it. You stop owning the runtime entirely, and that's the whole trade at this rung. The middle rung has one entry condition. The SDK is a library for Python and TypeScript only. In any other language, you run the command line tool as a cipsascos with -p and output format JSON. Light the context band because owning the ring means owning what it forgets, and that's where it surprised Daniel. Inside a session, the conversation accumulates and never resets between turns. Near the context limit, the SDK compacts it, a step actually called compaction, summarizing older history to make room. So, an instruction you gave at the start can be summarized away. A rule that has to survive the run lives in the file on screen there. Claude.md reloaded every turn instead of remembered. And between runs, the SDK keeps the session, so you resume it and the model gets back the files it read and the work it already did. That's remember last week and resume after a crash, 2 of the cards Daniel never got to tick. Hooks arrive with that ring and they sit on its rim. A hook is your own code registered to run at one of those fixed points from the settings file printed there. What it buys you is deterministic. Certain things always happen instead of the model deciding they should. 5 points sit on the rim before a tool runs, after a tool returns, when a subagent starts, when one stops, and when the run finishes. The one Priya needs fires before a tool runs, and it's the one printed there pre-tool use. The handler returns a result. Allow the call, change it first, deny it outright, or ask a person. Asking a person is Priya's requirement exactly, since the deletion waits until somebody says yes. Now put 2 rules on the same point. Matching hooks run together and the most restrictive result wins. One deny blocks the call, whatever the others returned, so a hook can tighten a rule and never loosen one. Which means you can add a stricter check without auditing every check already there. One honest edge, because a half learned version costs marks. What's guaranteed is when a hook fires, not what it concludes. The handler can be a shell command or an HTTP endpoint, as predictable as your own code. It can also be a prompt printed there as type prompt, which puts a model back in the decision. So a hook is a deterministic place to put a check. Whether the check is deterministic is your choice. Take the managed rung, and Priya has one more question, and it's the plate under the ring. It runs in a sandbox, an isolated machine holding its commands and files, and that sandbox is either Anthropic's or yours. The plate also forgets because a managed session starts fresh and yesterday's run leaves nothing behind. Where the SDK rung resumes a session, this rung starts fresh unless you attach a memory store mounted into the sandbox as a folder. That folder is what the agent learned. Claude.md is what you told it. Now the plate itself. Self-hosting moves the execution band onto your infrastructure, and that half of the promise is real. The agent's code, the files it works on, and the connections it opens all stay inside your environment. Which is the answer when the desk's agent has to reach an internal service nothing outside can route to. Here is the sentence people skip on the same page as the one they quote. You moved the ring and you didn't move the middle. The deciding still happens on Anthropic's side, on what the docs call the control plane, because that's where Claude runs. So there are two channels. The connections your sandbox opens stay under your control. The channel carrying tool inputs and results back to the control plane doesn't, and it has to exist. The model can't choose the next step without seeing what the last one returned. That's true at every rung, because wherever the ring sits, the middle stays on Anthropic's side. So Priya's rule isn't answered by picking a sandbox. The question is what you let a tool hand back. Back to Daniel's 3 weeks, and the 4 options are drawn now. Option 1. Keep extending the custom loop as gaps appear. Option 2. Move the agent onto the Claude Agent SDK. Option 3. Put the rule in Claude.md so it's reloaded every turn. Option 4. Run it on a more capable model that deletes things less often. Name the decision, what runs. Then read the stem as 2 demands because the answer has to meet both. A list of capabilities they'd rather not build, and one hard guarantee, must never. That guarantee is rule 2, the guarantee rule. When a stem says must, never, or always, guidance loses and mechanism wins. So, option 3 dies first on rule 2. That file survives compaction and it's still instructions, which is a request. A request can't hold a never. It works most of the time, which gets you to the day it doesn't. The more capable model dies on rule 1, the constraint rule. The stem names its constraint, and the answer is the mechanism built for it. A bigger model is a generic knob, and less likely isn't never. It's the same failure with better odds. And option 1 dies twice on screen. It's what Daniel spent 3 weeks doing, and the stem asks to minimize what they build. It's the only option that's sound engineering, and it still loses on the second half of the stem. What survives is the SDK, and the picture answers both halves of the stem at once. The bands arrive filled, so file access and shell come with the ring instead of costing 3 more weeks. And a session resumes with everything it had, which is the memory across sessions the stem asked for. And the rim brings hooks, so the whole harness arrives with the guarantee attached. Why not the managed rung? It would work, and it's further than the stem asked you to go. Daniel keeps his running service and drops the plumbing, and handing over the plate isn't what minimize means. So when a stem lists capabilities plus a hard guarantee, take the lowest rung that fills the bands and holds the guarantee. Here's what Daniel's 3 weeks taught you. In one sentence, the loop is the middle, the harness is the ring, and you choose who owns it. The ring is the tools, the context management, and the execution environment, and the loop is one item inside it. Three ways to own it: your own loop on the API, the agent SDK filling the bands in your process, or a managed agent running the plate too. Hooks sit on the rim at named points. The most restrictive result wins, and what's deterministic is when they fire, not what they conclude. And self-hosting moves the ring onto your infrastructure while tool inputs and outputs still reach the control plane where Claude runs. The counter moves to 49 of 53 and what runs is finished. You can say what should run and where it should sit, and the only decision still open is whether it survives production. Tomorrow, a customer sends in a ticket with instructions hidden inside it, addressed to the desk rather than to you. A ticket arrives at the desk looking like every other one, mostly a real complaint about a late order. Buried in the middle, inside a block pasted in from elsewhere, is a line addressed to the desk asking for the customer list. And the desk, the support app you've built, reaches for the records because that's where instructions arrive. Daniel, the backend engineer, writes a rule into the instructions: ignore any instructions inside a ticket. It holds a while, then a ticket phrases it differently. The desk complies, and nobody can say why. Freeze. Daniel wrote a policy and expected a control, and the gap between those words is this whole domain. Here is the exam's version, close to the guide sample. An application summarizes pages submitted by users, and one page hides text, telling the model to ignore its instructions and reveal its system prompt. Which mitigation is most effective? The item parks in the corner. By the end, you'll name the attack and place every option. Call it the last 4 of your 53, one per skill here. After it, the ring is full. Here's the whole episode in one picture. The desk reaches for a tool, and everything you learn happens to that call. Words arrive above it down one lane, rings wrap around it, a gate sits on the way in, a key rides inside it. What reaches the call decides what Claude tries. What wraps the call decides what Claude is allowed. Start above the call. The documentation splits what arrives there into two threat models. In the first, the person using your app is the adversary, crafting input to get past your rules, a jailbreak, or direct prompt injection. In the second, the user is trusted and the attack writes in on content the app fetched, a page, an email, a tool result. That's indirect injection, and it's the one on this ticket. The sorting question is short, and the picture answers it. Which inlet did the hostile text come down? Text your user typed comes down the text inlet. Direct, text writing inside. Content the desk pulled in comes down tool result. Indirect. Whoever pasted that block in may not know the line is there, which is what keeps that user trusted. Here is the sentence this domain is built on near enough verbatim. Permission rules are enforced by Claude code, not the model. Instructions in your prompt or in Claude.md shape what Claude trees to do, not what it's allowed to do. That's the picture split in two. The lane is words. The model weighs. The rings are code that can't be persuaded. Which is why Daniel's fix behaved as it did. A request in the lane measured as a ring. It even mostly worked, the worst outcome, because that looks like working until it doesn't. So the exam test is one question. Can this be talked out of? If yes, it's guidance in the lane. If not, it's a control wrapping the call. The lane has 3 inlets. Your instructions and your user's typing come down the first two, printed as system and text. Third-party content goes down the third, the block printed as tool result, never into your system prompt or plain text. Claude is trained to treat instructions in a tool result with skepticism, so the inlet carries meaning. It runs both ways, which gets tested. Your own instruction in there may be ignored or flagged as an injection. So your instructions go in your next message after the tool result block, never inside it. Assume an injection lands because one eventually does. A guardrail is any layer between it and something worth losing, the customer list. These 4 rings are the layering, And the order isn't decoration. Each ring inside the last sees more. Only three of them enforce. The outermost ring is least privilege decided before any call exists. Don't give the desk secrets it doesn't need. Scope permissions tight. Done properly, an injection that lands reaches a call that can read one order and not the list. The next ring works on what comes back out. The desk's fetched page goes to a small classifier call before it reaches the lane. It answers in one field, and a true answer returns an error or a stripped summary. A model judging text can be fooled, so this ring reduces risk and never enforces. The ring pressed against the call is your permission rules written in settings.json reading this call's arguments. Their order is exam material, deny first, then ask, then allow. First match wins, and specificity doesn't reorder it. A broad deny beats the narrower allow drawn beside it, so a deny rule can't carry exceptions. The innermost ring is the sandbox, wrapped around the command already running. You declare which files and network domains it may touch. The operating system enforces it, and the model isn't consulted. Look at the wall though, thick on writes, thin on reads, and we come back to that. Three of those rings enforce. Here is the one Daniel writes himself. The gate on the desk's path in hooks came up in episode 15, your code at a fixed lifecycle point, and the program running the agent acts on it. The one on this path is called pre-tool use. It fires before the call and answers allow, deny, ask a person, or defer. Defer hands the decision back to the program running the session. An interactive session ignores it. Post tool use fires after the call and can't stop anything. The tool already ran. The gate answers two ways: JSON on standard out with one of those words, or a bare exit code. Here is the fact most likely to cost you a mark. Exit code 2 blocks, and it beats even a JSON allow. Exit code 1, the failure code almost everywhere else doesn't block. The action proceeds. So Daniel's guard crashes, and the ticket goes through, and a mistyped path in settings.json disables the gate. The failure direction isn't uniform. A hook that shells out of your process times out and lets the call through. A callback hook inside your process times out and stops it. Outside fails open, inside fails closed. Here's the good news, and it's why the gate and the permission ring sit on one path. A call for the customer list has to pass both. The gate runs first, and exit 2 stops the call before the rules are read. A hook returning allow doesn't get past a deny rule, because the rules run whatever the hook said. The outermost ring said, don't keep the disk secrets it doesn't need. Here is the one it does. Keys live in a secrets manager, rotate on a schedule, and can be revoked and expired, never in a repo, never in a prompt. A key is scoped to a workspace, the boundary it can reach across, so a dev key can't touch production. That scoping is the identity half, which actor a call is made as, decided by you and not by accident. The strongest version leaves no long-lived key around. Your identity provider issues a short-lived token for the call instead. A key is created by a person in the console and shown once. Nothing hands it back. The admin API lists keys, renames them, switches one to inactive, and audits expiry. It can never create or reveal a key, so an option that fetches a key's value through an API isn't real. Back at the thin part of the innermost ring's wall, because reads are far looser than writes. By default, reads still reach the credential files sitting on disk. There's no built-in deny list, so only what you name in the sandbox credential setting is protected. Back to the page with hidden text in it. Option 1. Raise the model's temperature, so its behavior is harder to predict. Option 2. Deliver fetched pages inside tool, result blocks and scope permissions so an injection reaches nothing dangerous. Option 3. Add a line to the system prompt telling the model to ignore instructions that appear in fetched content. Option 4. Switch to a larger model that follows instructions more reliably so it holds your prompt against the hidden text. Name the decision, Will it survive production? Then classify the attack. The hidden text wrote in on a page the app fetched. So it came down the tool result inlet indirect injection. Now place each option. Option 3 dies twice and you watched it die. It's Daniel's fix aimed at a page instead of a ticket, still in the lane. It's documented advice and worth having, but the stem says most effective, and a request in the lane competes on equal terms with the hostile line. Raising the temperature dies on rule 1, a generic knob that's nowhere on this picture. Option 4 looks responsible and points the wrong way. The hidden text is an instruction, so a model that follows instructions better follows that one better in the same lane. Option 2 is the only one touching both halves of the picture, what reaches the call and what wraps it. Fetched pages go down the inlet built for them, and scoped permissions bound what an injection reaches. The other three sit in the lane or off the picture. That's the whole sort. Here is what the ticket and the page both taught you. What reaches the call decides what Claude tries, and what wraps it decides what's allowed. Security: two threat models sorted by which inlet the hostile text came down. Guardrails: untrusted content goes down the tool result inlet 3 rings and force. Screening only reduces risk. Hooks: pre-tool use gates the call, exit code 2 blocks while exit code 1 doesn't, and a call passes the gate and the rules. Keys and identity: a secrets manager scoped to a workspace, short-lived tokens over long-lived keys, a sandbox protecting only what you name. 4 ticks, 1 per skill, and the counter lands on 53 of 53. The fourth segment closes with it, and that's the blueprint. What runs, how it calls Claude, what Claude sees and says, and whether it survives. Every question they can ask now sits inside a shape you've seen. Tomorrow we walk the finished desk end to end at the pace the exam asks. "16 episodes ago, this was a pile of unread tickets and one API call. It now reads tickets, streams answers, knows what it cost, queues a backlog overnight, and reaches the order system. It runs an agent and refuses the hidden instructions the docs call indirect prompt injection. The ring is full, 53 of 53 objectives, and every one is something you've built. So there are no new facts today, only a new procedure. Every question on this paper points at one place on that desk, and finding the place comes before reading the options. 4 worked items at base. By the end, you'll have a procedure for reading a stem and an honest answer on whether you are ready. Here is the whole episode in one picture. Every stage of this desk is an exam objective. So find the place before you read the options, and the desk is your map. The left end is the call, one request, and a response carrying the stop reason which says why it stopped. Under it, the receipt, the block call usage, and the batch lane for work nobody is waiting on. The money lives here too, thinking billed as output and caching a stable prefix. Next along, what Claude sees and says, the instructions, the thread, and the answer leaving through a schema. 3 products read your instructions: the chat product, the coding tool with Claude.md, and the API with its system parameter. Under the desk, settings.json holds the switches and the managed ones bean. Then prompting context pruned instead of piled up and output shaped by output config format. Then what runs? A tool is a name, a description, and an input schema, and the description is the part Claude reads. A server when several apps want the same tool, a workflow when you can name the steps, and an agent when you can't. Workflows come in 5 named shapes and they're printed on the sheet. The right end is whether it survives production, the traces, the review, the guardrails on the way out. Every response carries a request ED. The string support asks for when you report a bad one. A quarter of this paper is ordinary engineering discipline, on it whether Claude existed or not. 2 rules have been killing distractors since episode 1. Here they are as a procedure. The constraint rule. The stem names what's binding it, and the answer is the mechanism built for that thing, which makes a family of options, distractors on site, a dial, a model swap either way, an output cap, a prompt line. If an option would fit almost any question in the domain, it isn't the answer to this one. The exception is worth marks when the stem's constraint is the model or the dial, choosing it is the mechanism. The guarantee rule fires on a word rather than a topic. Must, never, always, cannot. When a stem uses one about what the model may do, anything needing its cooperation is out and you want what holds without it. A line in the system prompt is a request. A hook at exit code 2 and a permissions deny rule in settings are controls. One habit before the items, most of a stem is scenery. Three parts decide it. The constraint, any must or never word, and what the stem forbids you to change. Here is the move that makes both rules usable. The four regions are a sorting table you run before the options. Say the four out loud because they are four regions of that desk. The call, what Claude sees and says, what runs. Will it survive? Name the region a stem stands in before you read the options, because each one has its own favorite wrong answer. One slot's penciled in already. Call questions get offered a knob. Rule 1 struck through row. The other three sit empty, and the four items fill them in. Four items at the speed you'll meet them, one per region left to right. At the call, cost is dominated by a large style guide sent with every request, and the model can't be changed. The constraint is on the input side, and the cannot is about what you may change, not what the model may say. So this stays rule 1. A cheaper model is forbidden by the stem, and shortening user messages moves the small part, while the big part repeats. Sending the guide once and referring back to it fails because the API keeps no state, so every request ships it all again. What's left is caching the part that's identical every time, marked with cache control. Call region, and it fills its slot with a knob. The wrong answer this region keeps offering. In the thread, an assistant answers well early, contradicts itself 40 messages in, and the product needs long threads to stay coherent. See and say and no must word anywhere. So this is rule 1, and the constraint is a thread that keeps growing. A bigger window is a model swap, and repeating the key facts every turn adds more of what's already too much. Dropping the oldest turns is the near miss. It frees room and throws away the facts the thread still needs. Summarizing the older turns and carrying the summary forward keeps them, which is compaction. See and say fills its slot with tokens instead of facts piled on or thrown away, and the docs call the damage context rot. Out where the tools are, an internal tool must be usable from 3 separate apps and maintained by one team. There is a must in that stem, but rule 2 fires on a must about what the model may do or say. This one's about where the capability lives, which is topology rather than behavior, so it's rule 1's question. Copying the code into each app leaves 3 copies to maintain, which is the constraint it fails. Pasting the data into each prompt supplies facts rather than something callable. A skill is a folder with a skill.md inside, and it carries knowledge where the stem asked for a callable tool. A server declared in .mcp.json is the mechanism built for that constraint. What runs fills its slot with the capability in the wrong place. At the edge, an assistant must never include a full account number in a reply, even if the customer asks. Must never about what the model may say, so rule 2 is on site and the region is will it survive. The prompt line is guidance, and the lower temperature is a dial, so rule 1 takes that one too. The weekly review finds it after it's gone out, and detection isn't prevention. What's left is the check on the way out, backed by a schema with no field to put the number in. The schema guarantees the shape and never the content, so the check at the edge is what enforces it. And survive fills the last slot with a written policy where a control was needed. 4 items and the table's full, which is the thing to carry into the room. The 2 rules did most of the killing, and 3 smaller ones finished the job. Detection isn't prevention, data isn't a capability, and knowledge isn't a callable tool. A last look at the Wandsworth marks walking the desk left to right. At the call, once caching is on, the response reports input in three parts: read from cache, written to cache the rest. The field called input tokens holds only that last part. So the tokens you sent are all three added, though the cached read builds cheaper. Down in the batch lane, results come back in any order, so you match them by the custom ID on each request. Under the disk, the file your coding tool reads claude.md arrives as a user message rather than the system prompt, so nothing in it outranks a later user turn. And for hard enforcement, you want settings and hooks. Also under there, a dateless model name is a fixed snapshot now, not a pointer to the newest, and the docs call that a misconception. In the thread, more context is not more informed, and past a point accuracy falls as the window fills. On the way out, pre-fill, the trick of starting Claude's reply to force a format is refused now and output config format replaced it. And that shape guarantee is why a refusal, a truncation, or odd casing all still parse as valid. At the server, an MCP server is more than a bag of tools. Tools are model controlled, resources app controlled, prompts user controlled. At the agent, multi-agent costs several times the tokens and wins in three situations: context pollution, parallel work, and specialization. A self-hosted sandbox moves execution onto your machines, so it buys where the code runs, not what leaves. Tool inputs and outputs still reach the control plane, which is the side where Claude itself runs. At the edge, a pre-tool use hook blocks the action with exit code 2 and exit code 1, which means failure almost everywhere else lets it through. Ready isn't a feeling, so here is a test per region you can fail. At the call, can you say what you are built for, what the three input numbers mean, and when you take the batch lane, see and say, name the three products that read your instructions and what you'd prune before you add. What runs, given a task, argue for a workflow over an agent, and name which of the five shapes it is. Survive, name one control that holds if the model stops cooperating and what a request ED is for. Four yeses and book it. One no, and you know which episodes to go back to, which beats a score right now. Two or more, and don't book it yet. That's the test doing its job. The mocks in this pack tag every question by domain and by decision, so a wrong answer names where on the desk it came from. That's the course. The four decisions are a sorting table you use before the options because each region has its favorite wrong answer. Rule 1 takes the generic knobs and Rule 2 takes anything the model has to agree to. And a quarter of this paper is ordinary engineering discipline, which most people revise last and lose marks on first. You built the whole thing. Every objective on that blueprint is a decision you've already made on a desk, Go and sit it.